we frame a network, right? One thing to remember with connectivity is we can study it at various levels. We can study it at neuronal population level. We can study it at the level of whole networks. So in a way, you want to remember that when you say network, it's a relative term, how you define your pathways and how you define your units. They can be abstract or fleeting, as is the case for some of the resting state networks sometimes. So connectivity in neuroscience has been around for actually quite a while. 1881, Golds argued that cognitive functions in the brain and motor functions in the brain are integrated across the brain, which implies a connectivity type of framework relative to the segregation of function where modular organization dominates. Now, we don't have too much in terms of publications or the use of the term connectivity until a little bit later, really the 1990s. And so why is that? Well, you probably have a good idea. Some important developments around the early 90s with the development, the discovery of really the bold signal DTI techniques, and also the analysis techniques. So that's Friston, Horowitz, McIntosh here, Biswell as well, to analyze that data and extract connectivity information from the brain signals, right? And that this development is actually quite important if you think about it, because it allows us to move from architectonic analysis, neurophysiological recordings, which are typically done in the animal model, to studying these issues in vivo, in the human or non-human primates, right? So we can produce these beautiful images within a living, breathing human being without having to cut them up. So that's important. It makes it easier. More people are doing it. We have, of course, two broad categories of connectivity. There is a third one, which I'll mention. We have structural connectivity, which, of course, describes the axonal myelinated pathways for the most part, linking cell bodies, right? And these we discover through tracing methods, DTI, DWI. You'll hear a little bit more about dissections. And then we have functional connectivity, which I'm discussing today, which really is sort of an abstract phenomenon. It's kind of not a real thing at all, because it's 100% statistical connections, right? That's how we quantify it. This is correlation, coherence, mutual information. And this is also why in this image, the arrows between the different regions are bidirectional, right? Because we don't know which way the information flow. We just know that these regions co-do something, co-activate, right? But we actually don't know whether information flows from V1 to 7A or back again. And to do that, we'd have to enter this realm of effective connectivity, which you'll hear about next week, of course, causal modeling, in which we can discover the strength of the pathway information flow in one direction or the other direction. So a subtle but very important distinction in sort of understanding what your data can tell you. And you'll see, especially with the PPI and some of these methods, we imply we want the information to flow in a particular direction. So there's a top-down influence on a sensory region. But in most cases, we actually don't know without further testing. Jump in with questions, by the way, guys. I'm happy to address them as we go along. So here's my bird's eye view of methods, which I always find is helpful. This is a modified, inspired slide from various other people. But it's helpful, I think, because there are a lot of methods out there. That's why you're here. So on the y-axis, we have the spatial scale of the network from just 2 regions, 2 units, to most of the brain, and then the degree of causal inference, so how well can we infer which way the information is flowing from left to right. In the top left, we have these broad methods, ICA, PCA, graph analysis. I also put anatomical modeling here too, because it sort of falls in here, where we can model the whole brain, but we really can say absolutely nothing about which way the information flows, right? So that they're really almost architecture type of analyses to discover the architecture of the connectivity, whether anatomical or functional. In the lower right, we have the extreme, where in most cases these are models, they're model-based techniques, and we have relatively small networks, so a handful of units, but we can perform experiments or analyses that allow us to infer which way the information is flowing, okay? In the extreme left and right, top right, we have sort of the extreme situations of bivariate correlation, no inference, just 2 units. In the top right, we have efforts like the connectome in the virtual brain, where we try to model the whole thing, including the direction of flow, including enhancement and suppression, inhibition, etc. Pretty cool efforts. Now, we're somewhere in the middle today. So this is where I put PPI, partial least squares, also machine learning. And it's in the middle because it can really apply to just a couple of regions. It can apply to a larger network. It doesn't tell us about causality, path of information flow, but because we're looking at connectivity across context, across different tasks or different situations, we're starting to acquire the information we need to create good testable models for those causal analyses. So I put them sort of in between. So far, so good. Okay, so PPI, as it's known, psychophysiological interaction, is a relatively straightforward idea in principle. So here's this was introduced 20 years ago now by Carl Friston in an experiment in which participants looked at dots, moving dots, and they were actually just dots, and they were trying to detect change in motion. That's it. And the idea is that we might want to know how the connectivity between V1 and V5, any 2 regions, changes as a function of X, where X is some context, some task, something relevant to behavior, to real human phenomena. And so in this case, it's attention. So does the connectivity between these 2 change? And you see that even in these slides, there is a little arrow. There shouldn't be an arrow because we don't know that that's the case, but we tend to do it. We just do it. We just want to know. And so in his example here, we see, well, in the case of attention, the 2 regions are more strongly correlated when participants are not attending to anything particular about the moving dots. Okay, very simple experiment. So how do we extract this information? How do we test this? Well, it's your GLM model, which you now, I think, know very well after Martin's lectures. It's a straightforward idea. We have 3 regressors, and the psychophysiological interaction, the PPI, is in fact an interaction term. That's all it is, right? So in this case, we'd have a task regressor, so something modeling the psychological phenomenon, the context here. In this case, it's attention or no attention. So blocks of attention, blocks of no attention. We have a region of interest whose activation, whose time series we will input into the model, in this case, the V1. And then we have the interaction, the dot multiplication between the 2, which will test the hypothesis of which regions in the brain in their correlation with V1 vary as a function of attention or non-attention. Sorry, that's a badly formed sentence. So that's it. That's all it is, right? Relatively straightforward. So it is a test on the slopes, the slope between V1 and some other regions as a function of context. Okay, in this case, task. And while it's a relatively simple idea, as long as you're comfortable with interactions can be a little tricky because you can't always detect them, right? So there are some little obstacles or, I guess, challenges that you have to keep in mind when you do this type of thing. One of them is that PPIs can be susceptible to issues with collinearity in the model. So here we see an example on the left. This is a non-factorial design, which I'll explain in a moment. We have activation for V1. We have our task regressor or psychological regressor, so-called, attention, non-attention condition, attention condition, non-attention condition. And here's the interaction. And if you just look at it by eye, right, you compare this with the psychological term, they look identical with a little bit of fuzz around the actual block here. And so what does that mean? It means they'll be correlated. And that's what's actually shown below here. It's 0.97 correlation because I made these up, of course. So what would happen with the model, with the GLM in this case? So what's wrong with collinearity? Pardon me? It's redundant, right? So the model is going to have a hard time fitting the regression coefficients. They'll be unstable. If the model actually finishes, you might get an error message that it can't do it. But at the very least, it'll be unstable. So here's another example, a small modification to the design where now we have an attention, non-attention condition. But in this case, the speed of the dots actually varies. So in some attention and non-attention conditions, they move quicker, and some they move faster. Okay, so what we've done is we created a factorial design where now we have two variables. One is attention, one is speed, and they're perfectly crossed, so they each occur in both levels of the other. And now we create the multiplication of the two, the dot multiplication. We have our interaction term, and you can see by eye they look different, and by nature of how they were formed, because it's a factorial, they are uncorrelated. So now we have a good stable model, right? In many cases, our designs look like this, and in this case, you may or you may not be able to detect your interaction depending on how closely these two are correlated. If there is variance, let's say in a big block design and there's a lot of wiggling around here, that it's sufficiently different from this, you'll actually be okay. The model can perform fine. In an event-related design, or a certain situation, you will not be okay. And so ahead of, you can't always apply PPI analysis to data you already have, because it just may not be set up quite right for the model. Does that make sense? It's subtle, but it's actually quite important because it just won't work. A related issue, so this is just a summary, a collinearity in the model will decrease the power of detecting our interaction term. And this is a little bit how to, that I just copied from actually Jesse Rissman's slide from a couple of years back. So sometimes what people do is they have two crossed independent variables. They identify their seed region, their region of interest, using one of the factors, let's say speed, and then replace the factor speed with the activity of the seed, and they're modeling the main effect of speed using the time course of the region. Okay, which brings us to the idea of main effects. So in all these models, we of course have to include the main effect of the region of interest, so just activation, correlation with the seed, as well as the psychological regressor itself. This is intuitive, although if you're not familiar with these models, you might skip it, and that would be a bad thing, because clearly, let's say if we skipped the psychological regressor here, attention, no attention, we just forgot to include it, the interaction term would still be significant because it looks very much like this, and so it'll be capturing the same variance, and then you'll be picking up an effect that you can't entirely interpret in terms of whether it's coming from this interaction term, this change in the correlation of a region with other regions, or the response of, let's say, the seed, the actual region of interest, to the stimuli. So that's an important thing. You do have to parse those. And that's why interactions are tricky, because you're parsing variance, and you have to make sure that the design is built such that even when you remove those main effects, you have variance remaining to test the interaction. Another way that PPI has been used is for pre- and post-intervention and subject group studies, where we don't have any kind of a psychological regressor, we don't have a condition, we don't actually even have an interaction term, we simply test the connectivity of a region in two groups. And so group in that case becomes our psychological regressor. And we're saying, okay, well, how does the correlation of my V1 change between patients versus non-patients? Here's an example, and it's a nice example because it shows two different things. And in this case, this is the connectivity between amygdala and prefrontal cortex as a function of depression-correlated genotype. So that's what is shown here, LL, LS, SS. And we see that the interaction term is higher in two groups relative to the one group. So we may say amygdala is more strongly, more weakly connected, correlated in one group than the other two groups. And that may be true. What's really nice here is that we can also look at the influence of the main regressor. So in this case, it turns out we also have a task where participants are looking at stimuli. Some are aversive, some are pleasant. And it turns out that amygdala actually has a differential response to the stimuli in the three groups. So it actually has a lower response in the group of interest, right? So what does that mean? It means that without including a regressor, a main effect of task, of actually just responding to these stimuli, we will detect a significant response to the amygdala regressor, regardless of whether it's actually a change in connectivity with the prefrontal cortex or whether it's a response driven by the presence of the stimuli on screen, because that response itself varies by group. Okay, so that's why it matters. That's why main effects matter. You just can't tease them apart if you don't include it. Relatively straightforward idea. Good. Now, in event-related designs, PPI is a little bit tricky, not impossible, but a little bit tricky, largely because of low power. As you know, we have a smaller signal in the event-related design. We also have poor model fit because we're fitting a response function versus the block design sort of reaches a plateau and we're basically fitting a block function. So it'll fit better in most cases. Versus in the event-related design, I don't know if you talked about it, but the HRF varies, and it varies by region and various factors. So we have more variability, smaller signal, and then we're layering on top of that the structured variability that we introduce due to a task, let's say, that we want to pick up with this interaction term. In addition, we know that the hemodynamic response function actually affects the interaction term such that if we simply multiply the time series of two regions, which by definition are neural activity convolved with an HRF, so that's this, the product is a little different than if we actually look at the interaction in the neural activity of those regions and then combine that with the HRF, which what you actually want to do to model what's actually happening in the brain, right? Because the HRF comes second. And that's what's shown in this picture. A and B are just the product of these two different, correspond to these two different ways of creating the interaction term. And the point is that they're different. How different and how much it impacts your modeling, your fit, depends on the design to some extent. The effect will be greater, obviously, in an event-related design where you have these brief events relative to a block design where you have a relatively sustained, sort of maxed out response, right? So you're protected a little bit with a block design. So in fast designs, you just have to be careful and really check what's going on and be cognizant of what's going on. And you'll hear from Dr. Rissman later today, I believe, about an alternate approach with the beta series correlation, which you can consider in those cases, in which you actually model each individual trial, get a regression coefficient for that trial, and use that in your correlations. Not impossible, but just a little harder. So what you'll see now is something a little different than was proposed by Carl Friston in '97, which was the subtraction model in which the psychological regressor is actually modeled as a subtraction, right? So you have attention, no attention. You can see that the zero line is somewhere in the middle. And the interaction term is the interaction between this difference and the time series of a region of interest. It's perfectly accurate. It's a little tricky in a couple of ways. One of them is that when you have the subtraction, it matters where you put the mean. So if you mean center, if you put the mean really at the mean of all the time points, and you happen to have more time points, more TRs for the attention condition, that'll shift where your mean is, and it changes what your regressor looks like, obviously. And so now you're weighing one condition more than the other, which you don't want. So typically you want to place the mean at the center between the max and min. And that's true, I guess, for all models. It's not particular to this particular case. The second issue is that this original subtraction model makes interpretation a little tricky, because if we have an significant interaction term, we don't know where it's coming from, and we don't know, we can't test that without going back to the raw data and actually plotting and doing a little bit of investigation, which ends up being kind of tricky in an event-related design. So when we have a significant interaction term, we just don't know if it's because, and it's positive, for instance, we don't know if it's because the slope in condition x1 is positive and 0 in x2. We don't know if it's actually 0, if it's non-existent in the first condition and negative in the second condition, or if it's actually positive and negative in each condition. Okay, so it's subtle, but for interpretation, obviously, this is relevant. This is what you want to know. So the model you'll see used typically these days is referred to as the generalized PPI model. It's a small modification. Jeanette Mumford developed this, or made mention of this some years ago, and then Don McLaren published it independently in 2012. Small difference, so now we're just simply parsing apart those two condition terms. They're included as separate main effects in the model, and we have an interaction term for each condition. So x1 may be attention, 2, this might be non-attention, right? So now what we can do is we can test the interaction by comparing the regression coefficients for the 2 interaction terms, and we can also explore them independently to understand which way the slope is going. So it kind of helps you a little bit in interpretation, really. So far, so good? Straightforward. Good. Another implementation, and actually in the original 97 paper, the proposal was really not just for psychological interaction, it was also for this so-called physiological interaction. So you may want to ask, does the correlation between V1 and V5 vary as a function of activity in parietal cortex, right? You're starting to test hypotheses about your model, setting up for a test of the causal connections. You want to sort of test which way to draw your lines in the causal model. And so here he showed with 2 different regions, the correlation actually changes drastically. This is a plot between the interaction term and the V5 response for a region in parietal cortex, but in 2 different regions, just a little off from one another. This hasn't actually been used that much in the literature, so you won't find too many examples of it, but it's something you can do if you have the right hypotheses. One thing I found was from Dee and Biswell. This is shown here. Just so you see how this might look in real life, is here we have two seeds now, right? So we have our left and right motor cortex, and our interaction term is just the dot multiplication between the 2 of those. And what we see is that there are these regions in red. How do you interpret that? Well, what you would say is my left motor cortex, actually either motor cortex, when it's active, when the other region is active, this region will be connected with these regions positively. It'll be correlated positively, okay? Here's another example in which we have our 2 interaction terms are right hemisphere prefrontal or parietal cortex seeds, and now we would say when one of these is active, the other one is negatively coupled to the regions on the other side of the brain. Okay, that's how you interpret it. It gets more and more hairy the more you have of these, but you can see sort of how you would implement this technique to test specific hypotheses about connectivity. Okay, so in a nutshell, PPI is it's a simple concept, somewhat tricky to use, but a simple concept. To study connectivity across context. And when I say context, this could be condition, intervention, group, activity of another region. Those are the examples I gave you. You could think of something else. It does require some attention to the model, inclusion of your main effects, regressor collinearity, and centering of your regressors. So you really do want to know what you're doing when you're modeling. And typically limited to a single region only because it gets more and more complex, but you can certainly do more. And of course, what I started with, the direction of the modulation is ambiguous. Here it's exemplified explicitly. So what we're assuming here is that the connectivity between V1 and V5 changes when attention changes. This arrow shouldn't be here, of course. We all know that. But it could also be the case that, in fact, the effect of attention on V5 changes when V1 is active through some other intermediate indirect pathway, set of pathways possibly, right? So we just don't know which one it is until we go that extra step and do the causal modeling, right? And this could even flip, right? So the effect of attention on a V1 could change with the level of V5. And what that means, I don't know. Whatever the model, whatever's going on in the brain. So, all right, good. Questions about PPI? Yes.
So how is this different, the PPI, from mediation moderation model?
It'll be similar. I'm not the right person to ask. I have a pretty good idea of how mediation moderation is implemented in a regression model, but off the top of my head, not 100%. I would ask Martin Lindquist when he's here in a day or two. Okay. It's a similar idea. I don't know that you explicitly test here what happens to the correlation when you remove the effect of one region or context. So it's different that way. Mediation moderation will start getting a little closer to the causality analysis, where we have a the correlation between two regions, and then we can actually hold constant, remove the effect of another condition or region or whatnot, and see what happens to that original correlation. We're not actually doing that here. Maybe you can answer that question.
I know there's a SPM package for generalized PPI.
Yes.
Is there a package for FSL too, or can we do that in FSL?
I'll show you today how to do it in FSL, because there is a package for SPM, so I'll show you how to do it in FSL. And FSL takes a different approach. They actually kind of say, well, we're not going to really help you out with event-related designs because they're hard to do, and so you're on your own. Which has some rationale because it is harder to do, and they support just a simple interaction model, which makes more sense, or just an interaction term dot product multiplication for block designs primarily. But I'll show you how to implement that. Yeah. Yes.
When we typically do the PPI, we will do the deconvolution, and we also adjust for the interest. Could you comment on these two? What do they do as to the linear model?
So the first one, you said you correct for the HRF. What was the second point?
The first one is do the deconvolution.
Yes.
To put the HRF to the neural input.
Yes.
And another one is that we normally do something like adjust for the long effect.
The long effect?
Yeah, especially it's typically in the SPM. We normally, for instance, do a big F contrast and adjust the effect.
Okay, so the second one, I don't entirely know. I'm not sure. Maybe I'm just not following, what the specific thing is. So we can talk about that maybe a little after. The HRF that relates to this earlier slide that I showed you. With this business, right? So this is the paper that it relates to, where and this typically applies for event-related more so than block, simply because in the block design, your HRF is kind of plateaued, right? So it doesn't matter so much. It's a block. It's basically a square regressor. In the event-related case, the correct thing to do would be, which this was in 10 years ago, more than 10 years ago now, Gittelman showed, when you take the neural activities of two regions, which is actually what would be happening presumably in the interaction in the brain, you would want to multiply these first and then convolve that with an HRF, rather than simply multiply the time series of two regions, because they are in fact already neural activity pre-multiplied with an HRF. So he simply showed that the two are different, and so that's why most people in an event-related design will want to deconvolve first, multiply the time series, reconvolve again. Of course, that depends on the quality of your deconvolution, right? Because you're introducing another manipulation, another model. But that's the idea. Yeah. Yes. Lots of PPI question. Okay.
Could you talk more about removing the mean from the previous slide?
What would you like me to talk more about the mean?
I don't understand how actually it gets rid of collinearity problem.
It doesn't get rid of collinearity at all. It'll just, where you put the mean will affect what your regressor looks like. So, so you can see, for instance, that if you look at this regressor, the mean is at the middle, right? So let's say this is +5, this is -5, just for kicks. Now, if we move the mean up, or accidentally it got moved up, because we said we want a mean centering, then now you're weighing attention condition at, let's say, 0.25, the no attention condition at -0.75. So you've changed the way you're modeling reality. And so this may fit more poorly to your real data than this will. So that's all. It affects what your regressor looks like. So that's why the centering is important. One last one maybe, so we get to the other half.
So my question here was, if you only model x1 for beta1 x1 plus beta2 ROI plus beta3 x1 times ROI, you can have an insight on the direction of the effect, right?
Why?
Because you can see if it's a positive or a negative direction, right? So
that's just the direction of the correlation. not which way the information is flowing.
No. Yeah.
Right,
Just the
yeah.
direction of the correlation.
Yeah. Yeah, exactly.
Okay.
Okay, excellent. So that's PPI. So good to try, and I'll say this again later. But with specific hypotheses, it's a good tool. It's right there. It's modeling a lot of stuff in the data, so it's parsing the variance nicely. And here are two of the papers that are good guides. So the second method I wanted to introduce is partial least squares. You don't see it as much as, well, actually PPI isn't that common because it doesn't always work, but partial least square is a cool, different approach to the same question, so I like to show it. And the reason it's similar is because just like PPI or even machine learning, what it's trying to do is find a set of regions, voxels, that co-vary with one another as a function of X. Again, context, task, group, etc. But it's doing so in a slightly different way, which may suit you better depending on what your data is. So unlike PPI, it's model-free. It's not modeling anything. It's sort of what falls out, falls out. And it's multivariate, unlike PPI, which buys you power. Very different approach, which essentially boils down to singular value decomposition of the cross-block variance matrix. So what is that? If we look at the variance in your data set, and you come up with a covariance matrix of all the activation between all the voxels. You would have a voxels by voxels matrix. And if we did an SVD on this matrix, you would have what's known as a PCA, more or less so, okay? So if you know what PCA is conceptually, that's what you're doing practically. If we ran an SVD on the within block variance for the task conditions, we'd have a big covariance matrix. Let's say we have many, many conditions, as in some, let's say, psychological tests. We ran a PCA on this. This would be a little bit like when we do a factor analysis and look for factors between behavioral measures, if you have many, many, many of those. When we run an SVD on the cross-block variance matrix, so this is the activity in voxels across task conditions or events or whatever your other dimension represents, this is a partial least squares analysis, okay, and that's why it's partial least squares. What does SVD actually do? What it does is it takes your data and which is voxels by conditions, and it decomposes it into what are called orthogonal basis functions, which you'll hear about quite a bit more. In this case, they're called latent variables, but the terminology doesn't matter so much in this case. And what a latent variable is composed of is three pieces. There are three matrices that are produced. Here we have a set of columns which have weights for the condition dimension. In this case, it's a condition, so let's say it's weighing heavily the first two conditions, negatively the next two conditions. And then we have this wide matrix where a row will represent the corresponding weights for the voxel dimension, so basically your image. These two are correlated with one another, so the interpretation follows that this particular latent variable, which you can think of as like a component if you're more familiar with PCA or ICA, we would interpret this to say, as these regions increase in activity together, in a multivariate sense, there's more presence of a condition. Sorry, that's badly worded. So that's to say, in these two conditions, these regions are more active than in these two conditions. Okay, so you've pulled out a relationship, in a multivariate fashion, between these regions that co-varies with some contextual variable, a condition. Very similar, right, to what we're doing with PPI, because we're looking at the variability or the change in connectivity between these regions, which is statistical association as a function of context. There's also this matrix here in the middle, which holds singular values, which represent the percent of covariance accounted for by this latent variable in the data. So they tend to be produced, like in PCA, in the order of variance accounted for. So not statistically independent, as you'll hear about in ICA, just produced in order of covariance accounted for. They are conceptually similar to PCA, ICA, and I would even say Fourier transform, because we're re-expressing the matrix into pieces, in this case, orthogonal vectors that can be recombined. So if you add these back up, you'll get the original data. This is a picture from a paper by Vince Calhoun. I'm borrowing it. You might see it again next week. But it's elegant in that it compares model-free versus non-model, model-based analyses. So we have our GLM and your ICA. The PLS looks very much like the ICA. We have a matrix here that we break down into, in ICA, it's a mixing matrix which represents time courses, and then spatial patterns for spatially independent components. And those are discovered based on a given criteria, in this case, statistical independence. The comparison conceptually, if this is not familiar to you, in the general linear model, we're actually doing the same thing, except we're going in the other direction. We are modeling the time courses. We're actually saying what we think the time courses are, and seeing how that fits, and that's how we get a spatial pattern or regression coefficients. So they're all very similar sort of beasts, just the direction we're going in and the assumptions vary. Okay. So here's an example from Spreng et al., for instance, in which they looked at autobiographical planning and visual spatial planning and accounting condition, and they looked at DMN activity, default mode network activity, and I believe dorsal attention network DAN activity, and they're showing that the DAN in red is more strongly active in the visual spatial planning condition than autobiographical planning. The DMN does the reverse, and then this is most strongly expressed about 6 TRs, 12, 14 seconds after the event onset. And then they showed that here's the frontoparietal network, which is more strongly co-activated. All these regions are co-activated in the planning conditions relative to the counting control condition. Okay, and this is pulled out in one go. It's just sort of pulled out because that's what the covariance is in the data. Didn't have to be, but that's what it was. There's one more EEG example. I won't go into it, but if you want to know how to do it in EEG, just let me know. The technique is quite flexible because, like for all these decomposition type methods, it depends on what the matrix is that you're starting with, right? It's a hammer you're applying to a matrix. So what you put in will determine the kind of results that you get out. So this is where we started with a matrix where we have conditions by voxels. You could expand the matrix, add a second group with the same conditions, and now we would be looking at the patterns of covariations between voxels that vary across people and conditions. So we might find group differences. We could also expand the matrix along the columns by including activity from each voxel in a window. So for, let's say, a set of TRs around an epoch. And now we're looking for the spatiotemporal profile set of voxels across time that vary across condition, okay? And that's, by the way, how they got these plots. They had a matrix in which they had space and time in their columns, and so they can look at the expression of this variable across brain regions, where we see FPN here, but also across the window following each event. Okay. We can also vary what we actually put as the data in the matrix. It doesn't have to be just bold levels, what we call activation. It could be, let's say, a correlation between the activation of a region of a voxel and performance or activity of another region, or an EEG signal, or symptoms, or reaction time, whatever you want. And then what you're looking for are voxels that are coupled to one another, that co-vary across conditions in their correlations. Okay, just a multivariate technique. And then finally, we can naturally combine them. We can include both the activation and correlations with performance, et cetera. And now interpretation would be that these regions are coupled to one another across conditions in their activity and their relationship to X behavior, let's say. Okay. So it's very much in your hands what you put in there, which is, by the way, true for all the other decomposition techniques as well. Minding assumptions about the data structure. And while it's model-free, there is, again, this little business of demeaning, which can influence in the same way as it does so for the GLM, for the modeling. It can influence what the model will see because you're manipulating what variance is the biggest, right, is most salient. And so that's what will come out. So we can demean in different ways. For instance, you see here, if our data look as such, where we have group 1, group 2, condition 1, condition 2. You can see a group effect, you can see a main effect. If we remove the group effect, if we subtract the group effect, you will be highlighting the condition differences because we're only seeing this little increase here relative to the mean and decrease here, and the same for group 2. If we remove the condition mean, we're going to be highlighting the group differences. If we remove the overall mean, both types of variance are in the data, and they ought to be discovered by the algorithm, right? Now, one nice thing about the implementation of PLS, at least in the one implementation, there are now 2, I believe, implementations, but the original one that was available, is that all the statistics are distribution free, so they're all resampling methods, which Martin Lindquist will talk more about, and Martin Monti as well. Permutation, which is shuffling of the assignment between conditions and subject, is used to test for the overall significance of a singular value, which means how much covariance is accounted for by a latent variable. So basically, whether you would get a latent variable that accounts for as much variance as it does by chance if you just shuffled completely the assignment of subjects to conditions. And then bootstrapping, which is resampling with replacement. So you're varying which subjects are in your sample, right? So you're kind of testing what your population is composed of, is used to create confidence intervals on the weights for each voxel or each condition. Okay, so we're not relying on any distribution here, which is nice. It's already implemented for you. So here's a summary of PLS. How am I doing for time? Good. Very similar in PPI to me in seeking task-related patterns of functional connectivity. However, it's a little different in that it's multivariate and more or less model-free. You're very flexible to incorporate time, covariate seeds, beta maps, etc. And you have a non-parametric statistical assessment, which is a nice bonus. It's already built in. You can always code it in, but here it's already built in for you, which is nice. And it has been since 1990. It may not, one thing that sometimes people don't like, it may not produce the contrast that you want. So you might not want to use it. But I found that, in fact, if it's not producing the contrast you want and the data look good, they're demeaned properly, everything's looking good, then it's probably a really, really small effect. Because if you're using a multivariate technique to really leverage the covariation between all these regions, the effect may not really be there. So you can switch to any technique you want. It probably won't magically appear with a different technique. But if you have small effects and precise hypotheses, I'll take that back. So for more on PLS, here are 2 papers. There are a ton of papers now on how to use this technique, and you can download it from Baycrest, Rotman in Toronto. It's MATLAB based. I'll show you what it looks like today as well. Very quickly, questions about PLS before I go to the last piece. Who's tried PLS? Handful. Okay, yeah, it's usually not as common, so hopefully I'm teaching you something a little different, a little new. Who's tried PPI? Yeah, that's better advertising. So here you have a different method, something different. Now, one catch. Originally, PLS was actually designed for between-subject analyses, whereas PPI, by definition, is for within-subject connectivity. Now, that doesn't mean PLS can't be applied in a within-subject way, but the papers you'll see for the last 20 years are almost all between subjects. What does that mean, and does it matter? So what do I mean by within-between? Well, within subject is across time for the most part, right? So we're creating a model for a given individual. We're modeling a time series, like for a seed analysis, for resting state analyses, or across trials. And that's where we're looking for correlation of a region with other regions. In a between analysis, we can look at correlations in the mean values of each individual, and we're looking at that correlation across people. Okay? And so PLS, in some cases, actually machine learning gets used in this way as well. Now, this isn't an issue unique to functional connectivity or PLS or PPI. It's true to any statistical analysis. We can look at within subject metrics or between subject metrics. So even when we look at, for instance, reaction time and bold correlations, activity correlations, often we look at them between people. We could analyze them within people. And why does that matter? Well, because they don't have to be the same across people and within people. And I think that's important depending on what your goal is with these measures and how you're going to interpret them. So does between subject variance recapitulate within subject variance? The answer is not always. by no means. And you could have a situation where you have a positive correlation between, let's say, your DMN, a visual cortex, and it's positive across subjects, and you say, oh, look, they're coupled positively. And you look within a given individual, and they're actually negatively coupled. And so what in the world is going on? Well, they will be the same if the two types of variants actually measure the same thing. So if the process you're measuring is consistent over time and across individuals, which is discussed in this kind of neat little paper as ergodicity, then you will get the same correlations. But of course, between subject variance has other stuff. It's between subject variance on top of it, within subject variance. So they don't have to be the same. And what's neat is to think about how this impacts your interpretation. This is a little example from Roberts et al., which came out in NeuroImage this year, where they sought to look at functional connectivity within subjects versus between subjects just to see how similar it is, and does it vary, does it not vary. So this is a correlation between, so they use AS for between subject as across subject. So when you see AS, these are correlations computed across subjects on mean scores for each subject. The within subject connectivity is the mean of within subject correlations. You've got your head around that? Does that make sense? Okay, I can explain that in a moment a little more if you're not sure. So what we see here is these are regions in the DMN that they used as seeds, and they're looking at correlation between these regions and every other voxel in the brain. And what they see is that those relationships aren't recapitulated well don't correlate between the correlations between subjects and the correlations within subjects. Sorry, too many correlations. Except for these red little regions, which are actually regions right around the seed. Those seem to correlate well between the two different correlations, which is probably to do with the smoothing around the region. So you're actually correlating the same thing. Here we see kind of a cool matrix, which shows this is two different conditions that they looked at this in, so past, future. Between subject correlations on the left, within subject correlations on the right, and these are correlations between regions of interest within either the DMN network or the dorsal attention network, okay? And what did they found? They found that they had better prediction for regions within network than between network. Prediction, I mean, between the two types of analyses, left and right, within, between subject. So you can see that if we look within network, this is relatively positive. So more red is positive, more blue is negative. So these correlations are overall positive within subject analysis, and they're overall positive for the between subject analysis. If we look between networks, so which is this lower left part of the matrix, so these are correlations between DAN and DMN regions. They vary a little bit more between the two different types of analyses, right? So this is blue, green around 0, and then red as well. This is sort of uniformly 0. Additionally, we see that the between subjects analysis here on the left has a lot more blue spots, right? So a lot more negative correlations than the within subject analysis, which is relatively uniform at either 0 or positive. And between subject functional connectivity is actually more variable, which means more variability in the magnitude of the correlation. So we have blue and we have red, and the intensity varies here visually, right? And in fact, what you also have is the strange phenomenon called Simpson's paradox, where, let's say, you look at this correlation here. These regions above the diagonal, by the way, indicate which of these correlations are significant, okay? So you have situations where, and so you can see, for instance, within subject, almost all of the correlations within a network are significant, between subjects, much less so, okay? And then you have these strange relationships where you have, let's say, the correlation between the right SMA and the right, I think this is MT, is negative in one case, positive in another. Okay, so you can actually get flipping of the correlation, which is perfectly reasonable. So here, this is what it looks like. So you can envision it in your mind. You have a percent signal change for the right SMA, percent signal change for the right MT, and you have a negative correlation across subjects. But if you look at the correlation within each subject, it's positive. Okay, so you can, and they were clear to know that this is the minority of these correlations. Most of them actually are at least in the same direction, but they don't have to be significant in both cases, and they certainly don't have to be in the same direction. So why am I showing you this? Well, because it's something we don't talk about a lot. And to me, functional connectivity analysis intuitively actually requires analysis within subject variants, not just between subject variants. And I think this is also somewhat good to think about in a time of big data, when everything we're encouraged to do is analyze monstrous data sets with thousands of subjects. Well, it sort of depends what your question is. Okay, what answer do you want from your data? Do you want it to be based on between subject variants or on within subject variants? You can do both, and then you're covered, then you're good. You're looking at both the within subject correlation, which I think captures something more inherent, more sort of basic about the relationship of, let's say, two regions. Saying something about their functionality, mechanistic functionality, and then how stable is that across a population, which is the second question, right? You need both. And this is, of course, not unlike hierarchical GLM modeling, in which we model an effect within an individual first, and then look at how stable is that across subjects. We pool across subjects. We don't typically go and do one condition in one set of subjects, second condition in a second set of subjects, because I'm sure, as you've heard, you'll be open to between subject confounds, right? And it's sort of the same idea here. And then I guess one last point is that this actually holds true for correlations with external variables as well, which we don't actually talk about too much. So most commonly we'll correlate bold activity with reaction time, and almost always we do that across subjects. And then we say visual cortex activity causes faster, slower responding. Maybe. Or maybe that's something, there is a between subject variable that's creating that correlation, you know. So the people with slower responses also have higher activity overall in all parts of the brain. There you go, and that's it. Okay, so something to think about in terms of interpretation. It's not wrong, it's just understanding what it means and how to parse the variance. And finally, which method? You know, so I didn't talk about MVPA because Jesse will talk about it, but I put it here because it's following shortly and it's related. So PPI, to summarize, kind of looks like this. We have this interaction term, and Y is our time series in the brain, any other region. It's a mass univariate analysis bound by the region of interest correlation across conditions. We're looking at this correlation across conditions. So we are testing functional connectivity hypotheses. We're using a model, and so this model is subject to usual standard regression assumptions. It's great for factorial designs if you have it, where you have large power, precise, sort of well-defined network hypotheses. It's perfectly good technique, very effective. Now, PLS is a totally different beast, where we have a multivariate analysis. So we actually have, if we had a regression equation, we'd have many, many voxels on one side and our conditions on the other side. And so we're looking to discover the combination of regions that do the same thing across whatever is on the other side. So let's say condition, group, etc. We're not controlling this analysis. So this is not a model-based analysis. It's based purely on how the covariance is distributed in the matrix. And then we have machine learning, which I add here for comparison. So you have the full list where we have, again, it's a multivariate analysis, but our voxels are now on the right. So they're actually the independent variables, right? They're no longer dependent variables, because what we're predicting is a label. This is, let's say, our condition. So we have a multivariate analysis, but the objective is very different. It's to predict the class label, and not to sort of study the correlations between these regions in their own right. So it's a different tool. It's a general prediction tool. You can use it with any kind of data. Okay. And I think that's it. Good, perfect. So that second part is crystal clear. Excellent.
Question already.
Thanks. This is actually, the second part was crystal clear. I'm going back to PPI.
All right.
Can you make it more complex? I mean, you're looking at a two-way interaction. Can you make it a three-way? In fact, can you have the physical, and the psychological, physical interaction within that design? Is it possible? Obviously, it's going to be harder to get, but is it?
It's harder to get, harder to interpret. It's possible. It's the same as in any regression model. If you have 3 conditions, 3 levels, you know, it's going to get harder and harder to tease it apart, because you'll want to include the lower level interactions. You know, so certainly possible. You can also do interaction terms between EEG data and region of interest data. You know, you can do whatever you want, really. It's really just the standard regression assumption. So, you know, are they collinear? Are they parsing the variance in such a way that you can actually interpret it? Yeah.
Just wanting to follow up on that. Can you do nonlinear trends, nonlinear covariance?
Well, regression will only test, I suppose you'd have to start introducing nonlinear terms, which would get interesting. I suppose in principle the answer is, of course you can. Just, you know, how is it going to behave? But yeah, in principle, I see no reason why not. So, Mark, you made a little change in the schedule. So does that hold, or are we doing the lab now? Or was that just sort of accidentally plopped in there? I'm happy to go straight. I have my 2 slides just in
Suggestion
case.
from the floor, which was that we can break up these long lectures by doing a couple of our truth or lies opportunities here. What do you think about that, Jesse? Is this something we're ready for? Should we do that for 15, 20 minutes and just...
Do you want to do that now or after the PPI lab? It's up to you guys whether you
It's all
want to
good.
break or whether you just want to get
All right.
through the material. Because it's exciting. Okay, awesome. So we can do it. I'll try to stick to it in an hour, and then you'll take a break regardless for the truth and lies. And I'll set you up for the truth and lies too. So this is not recording anymore, right? The labs don't.
Nope. There it is. We're going to turn it off.
All right. So now I'll tell you.
Looks like we have everybody back in the room. Thank you. That's really fun. I'm glad we're doing the bios and things. It's nice to sort of hear about people, and that's really good. So I listed this MRI primer as optional for people. You know, I think that some people come in with a fair amount of physics background and feel like they understand the basics. But this is a lecture on MRI basics, and I will not be offended if you decided this is the time you have to check your email. Nevertheless, it's always been the philosophy of the course, as well as of the practitioners here at UCLA, that understanding the method in depth from the acquisition end is exceedingly important in trying to understand how your data work. And so by the end of this, you'll have heard about pulse sequences and gradients and all the other jazz. And I love to be interrupted for questions. The interrupter, I think, is in the back row next to Susan right now, the microphone, so please feel free. Okay, so MRI is based on the properties of magnetic resonance, which themselves are based on the local properties of nuclear spin. And spin is a property of many particles, like gravity is a property of the world. And it is like a type of angular momentum, or at least metaphorically like that. And like angular momentum, it's a vector quantity. It's oriented in a particular direction. And it turns out that it's a quantum property, meaning that it's incomprehensible. Chiefly, the incomprehensibility here has to do with the fact that, that spin can exist in one of two conditions, up or down, but there's no transition between them. There's an indeterminacy about spin because it's at such a local level. Not all nuclei have a non-zero spin, but many do, and so we'll concentrate principally, in fact only in this talk, on protons, which have a non-zero spin. Oops, is that animation going or not going? I can't really tell. So we can think about a vector quantity along the axis of spin, and this is now a spinning top. And whoops, I don't know why the animation didn't start. I hope it will. Is my animation start? I can't even see from here what's going on that. It started? Oh, good. It requires more patience, apparently, than I have. I don't see it spinning. Do you see something going on over there? Anyway, okay, so I'm not going to bother with the slide level. Spinning tops, as you know, will maintain their unlikely orientation of, standing on a point, and that's because the angular momentum of the moving part of it is conserved. Angular momentum is conserved. However, they do tend to start to fall, and rather than fall directly, what they do is something called precession. And I'm sure you know what that looks like even without my movie in here. And the precession is the effect of conservation of angular momentum. If the top is slightly off center from the Earth's gravitational axis, then the vector describing gravity and the vector describing the angular momentum cause this precession to occur around us. Nuclear spins have exactly that same kind of property. Mathematically, it's described identically to describing angular momentum for nuclear spin. And as I mentioned, the spins can exist in exactly two states, one of them called up and one of them called down, and that is effectively the orientations with respect to one another. And if you place the nuclei, which have a non-integer spin, 1/2, 1.5, and so on, in a magnetic field, those spins align opposed to or against that magnetic field, and they do so with different energies. Because, in fact, the proton nucleus is a charged particle. And you can think about the spin as a moving charge, and as you probably know from basic physics, moving charges have a magnetic moment associated with them, and therefore it's in some sense not surprising that it interacts with a magnetic field. And so when you place these protons inside a magnetic field, they always precess about that magnetic field. Interestingly, they all precess at exactly the same rate given any single magnetic field. Basically, all protons are identical, so maybe that shouldn't be too surprising. And that rate is known to an extremely high degree of precision. many, many digits of precision, which is the proportionality constant gamma. But I guess this pointer is working on, do you see it over here? I guess you don't, okay. I can't move it to that screen. Oh, there it is, good, okay. So gamma is the proportionality constant between the magnetic field and the rate of spin precession. And it's approximately 42.58 million times per second, million rotations per second per Tesla of magnetic field. When an ensemble of protons is placed in a magnetic field, the individual spins adopt the up or down sign condition, and they each precess around that magnetic field axis the same rate, but either in their up or their down conditions. Let's see what we got over here. So you can think of each spin having a particular phase angle, which is its rotational state or rotational orientation around its precessional axis. And an ensemble of spins, they will each have their own phase angles, which may be different. And so if we were to think about the vectors describing now the transverse component of this, they'll tend to cancel out. But the vectors describing the vertical axis will add together, and because there's an energy difference between the number of spins aligned with and opposed to the magnet, if you add up the vertical components, there's a net magnetic moment to the whole sample. Okay? The transition between up and down states is an interesting thing. As I said, first of all, it's a quantum process. They exist in one or the other, but don't seem to go through any place in getting there. And protons are impossibly small, impossibly tiny mass. And you would think intuitively that you apply a magnetic field and everything would instantly organize. But in fact, that's not the case. In order to go from the up to down state, the protons require some sort of interaction with their environment, typically a sort of mechanical kinetic interaction, bumping into each other and so on. And not only that, but the amount of energy involved in those collisions has to be identical to the energy difference between up and down states, or it won't happen. Therefore, it's not that statistically likely that an individual proton will change states. It requires a lot of random interactions at exactly the right energy. And so it takes quite some time for the spins to move from their equally distributed state to their equilibrium energy state after you place them in a magnetic field. And that time, it takes place over the course of seconds, which is very, very long if you imagine something like protons, and because of the statistical unlikelihood problem associated with it. The rate at which the spins reach equilibrium is a mono-exponential, right? They don't ever really get there, but when they're far away from equilibrium, they start to move there quickly, and then they slow down as they approach equilibrium. And the mono-exponential time constant that describes this has the exceedingly clever named T1, which implies there might be some other T, and you're probably, of course, aware that there's a T2 associated with that. The T1s of different protons, of protons in different molecules are very, very different. And the reason for that is really having to do with how fast the molecules move. If you have molecules moving at an extremely high rate, like in water, and then most of the collision energies are at much too high of an energy to facilitate the transition between up and down state. If you have protons in a highly bound condition, like in proteins, then you have mostly low energy collisions because things are not moving as fast. And there's some middle range where this all takes place. And so for fat, you tend to have a very rapid T1, right? Which just the fat molecule, these hydrocarbon chains, like to wiggle at the right rate. Water, everything's moving too fast. And brain, someplace in between, principally having to do with the amount of structure in those molecules. Okay. I guess I already said this. So let me just quickly summarize then that spins tend to align along a magnetic field. and they precess around the magnetic field, and the rate of alignment is called T1. Now, it doesn't matter where that magnetic field comes from, the spins like to precess around it. And so if you were to make a magnetic field vertically, the spins would precess around the vertical field. If you make it horizontally, they precess around the horizontal field. If you add those two together, what do you think happens? Anybody? Magnetic fields added like that? They're just vectors, just tilts, right? So if you simply add a small magnetic field this way, they precess around that slightly different orientation. However, if you set up a situation where you've got a second magnetic field which is rotating at exactly the same rate that the spins are rotating, what happens is with respect to those spins, they see a constant magnetic orientation, right? So here's my proton spin, okay? And here's now my moving magnetic field. And you can see that with respect to the proton, that moving field looks stationary. So what do the spins do? They precess around that, okay? And so in order to, the phenomenon known as magnetic resonance involves the idea that I have the spins precessing, each of these green lines represents the orientation of an individual spin, okay, which is evenly distributed. And then I have a second magnetic field which I'm going to have rotating at the same rate as the spins. And what the spins then do is rotate around that field. So if you think about the combined magnetic moment from that, which is all vertical to start off with, it now starts to rotate. So this blue vector starts to rotate around my second field. Only if I'm moving at exactly the same rate as the protons. So that's the process known as magnetic resonance. However, what in effect you're going to do is take the large magnetic moment associated with all of those spins adding together along the principal magnetic field and rotate it. And once having rotated it, you now have all of those spins together, but they're still precessing at the same rate. So now I have a time-varying magnetic field which is just rotating around. And the magnetic resonance signal is just to put a conductor nearby. And if you have a time-varying magnetic field near a conductor, what happens? Anybody? Somebody? A current, right, through that conductor. And that's all. That's all there is to it. That conductor is conventionally called an antenna. And the coils that you put people's heads in are just wires that conduct a current through them. They're tuned a little bit so they like to conduct current at particular frequencies, in particular the frequencies that the spins are precessing, but that's the whole experiment. Okay. Now, once they are transverse and generating signal, remember that this signal comes from on the order of molar quantities of protons. And as it happens, they'll never be in absolutely the same magnetic field because they're in different places. You can't make a perfect magnetic field. So what happens is that initially all the spins will be precessing together, right? Because we've taken that vertical component and just brought it downward so it was all together. But now the individual spins are likely to experience slightly different magnetic fields associated with their position, so they dephase. And so initially, we get a large current through our antenna. It's sinusoidal because they're just rotating around. But as the spins dephase, that signal goes away. Okay? And the rate at which it goes away is called T2. Good. All right. So T2 simply describes another first-order rate constant for here. It's the rate at which we lose signal. Right? Okay, so let me just do a quickie animation from here. So here we have an individual proton rotating. And I'm just showing now a coordinate frame that's rotating with the protons. And you can see that with respect to that coordinate frame, the spins look like they're constant. So if we now sort of catch up with this, we're spinning at the same rate as the protons now, so things look stationary. Okay. So we can actually decompose that coordinate system into a vertical and horizontal component. And we could just sort of ignore the little ball that's the protons. And so we can see that now if we were to move away from it, stop spinning with it, now our coordinate frame is rotating with respect to us, but the protons look like they're in the same place with respect to it. Okay, so now I have an ensemble of spins, each of which apparently has a different color in the rainbow, and they are each individually rotating around the longitudinal field, okay? And they have horizontal components that are all rotating but in different axes, different orientations. So as a consequence, the net horizontal component is 0, and we just have the vertical component left. Okay. I have to sort of lean over to see my slide. I didn't do mirroring here. So now I'm going to produce a second magnetic field, which is rotating with the protons. How do we know it's rotating with the protons? Because it's staying still compared to that coordinate frame. And the protons all rotate around that second magnetic field. So here they've gone 180 degrees. Now we're just going to step back and watch it all rotate. And it's a more complex motion. It's gone 180, it's going to go down, and it's going to come back up. And so they just processed a whole 360 degrees around that rotating magnetic field. And that rotating magnetic field is what's generated in the coils in order to produce the MR signal. Okay, so the actual, in the coil, the magnetic field rotates around. Okay, so now we're going to do the process again and flip them only 90 degrees. And once we flip them 90 degrees, we can see that basically all the magnetization is rotating. But it's made up of a bunch of individual spins, some of which are going faster in green and some of which are going slower in red. And you can see that quickly that signal magnetization starts to go away. That's your T2 process. Okay? All right, so I'm going to skip this and move on to the next slide here. So now I've got all the spins processing around the principal magnetic field, all in the same place. They start to dephase from T2 relaxation. I've actually, by the way, written T2 star relaxation, which I'll describe in a moment. And then there's a trick you could do. And the trick is to go ahead and apply that rotating magnetic field again, but instead of waiting long enough for them to rotate 90 degrees, you rotate long enough, you leave it on long enough for them to rotate 180 degrees. So I take this sort of pancake of spins and flip it, okay? They're still rotating in the same direction, however. And so the green ones, which were rotating faster, have now been placed behind the red ones over here, which are rotating slower. And what do? They catch up, and you form what's called the spin echo. Okay? And the spin echo is an interesting phenomenon because regardless of how fast they were going individually, you still get them to come back together at the same rate. So all these different dispersions, the spins operating at different frequencies, get compensated for. Okay, so let me, I have to run through the animation manually to move to the point I want to on here. So let's see, we saw all that happen. Okay, now let's keep playing the animation. And the signal just dies away. Okay, but then I'm going to go ahead and flip that pancake 180 degrees eventually. Oh dear. I'm sorry I didn't tune that animation properly. Where does that happen? Apparently right in here. Okay, let's let that run a little bit. Okay, so signal is dying away because the spins are dephasing. I then go ahead and, after the signal is really crushed, flip the whole thing over. Okay, and now the green spins are behind, and the red spins are in front, so it all catches up, and that's the so-called Hahn echo, or Hahn spin echo, for which Erwin Hahn gained his Nobel Prize. All right, like T1, T2 differs across different tissues. And interestingly, the same tissues which have long T1s tend to have long T2s. There's a simple reason for that, which is that T2 cannot exceed T1. So if T1's very short, the T2's going to be very short. And there's also some non-trivial reasons why they are linked. But either way, T1 and T2 are positively correlated. And that has major effects on image contrast, which I'll describe. So water, which had a long T1, has a long T2, meaning its signal decays very slowly. Whereas fat has a short T1 and a short T2, signal, the magnetization recovers quickly but decays very quickly. Any questions at this point? Yeah, please. Yeah, there's a mic, I think in the back of the room. Kiara? Yeah, thank you. See, I learned a name. Actually, I've been working on your names for a while here.
Thanks.
I find that if you hit them harder, it works better. I'm kidding.
Creating some noise. I'm wondering if you could relate this to multi-echo acquisition.
Sure.
So I know that multi-echo acquisition, you're sampling different points of the curve of the T2 decay. And I'm wondering how acquiring those echoes allows you to really do that.
Absolutely. Okay, so good question. So let's go ahead and form our spin echo. Okay, I'm going to let that dephase and flip the pancake over soon. Hard to anticipate exactly when. Could happen at any time. Apparently it's going to happen quite some time from now. Okay. All right. So, whoops. Yeah, so that's the echo reforming, okay? But, so now everything comes all together, okay? And then what happens afterwards? They dephase again. So what should I do? I apply another 180-degree pulse, right? And it's going to come back, right? So that's the notion of a multi-echo acquisition. You can reform this echo repeatedly. Does that answer your question as it stands right now? There'll be more on this. Okay, right. So it's kind of a cool thing, and you can keep forming these echoes over and over and over again until something happens. And actually, let me just go ahead and say what I was going to say about that, which is that, remember the reason that the spins are dephasing, it's principally because they're rotating at different rates, and the reason they're rotating at different rates principally is the fact that they're in different magnetic fields because of where they are in the body. And there are other factors that cause them to dephase besides that. For example, they are moving around with respect to one another, and each of them is magnetic, right? So you might expect that their local rate of precession depends on how close they are to their neighbors, which it does. And so those factors are what tends to make the T2 different among these different tissues, are the amount of interactions between the protons. Okay? The rate at which they initially decay has to do with the stationary magnetic field in homogeneities principally. And we call that rate of decay T2 star, whereas the intrinsic rate of decay having to do with their interactions with one another we call T2. Okay? T2 star is more or less a property of the sort of physicality of the magnetic field, whereas T2 is a property of the sort of molecular environment and is somewhat more interesting in many cases. Okay? We explore differences in T2 by using these multi-echo sequences, because the signal on the second echo is going to be smaller than on the first echo because of the molecular interactions, and smaller again on the third echo, and so on. Okay? And so you can follow that decay, and we call it T2. All right, so how do we actually go about seeing these effects? And the way we explore T1 is by repeating the excitation pulses, these ones that rotate the spins from vertical to horizontal, at some rate which is not an infinite spacing between them. Okay? Remember, it takes an infinite time to recover completely, but we tend to use shorter times, like seconds. Here I'm imagining spins which are all oriented along the longitudinal axis of the magnet in complete equilibrium. We've left the patient in there minutes. Okay? You then apply a 90-degree rotational pulse, and it produces a signal which decays at the rate T2. If you then wait for some amount of time, the spins spontaneously reorganize and start to recover their magnetization, that T1 process. However, if the time between repetitions of our pulses, which we're going to call TR, is relatively short compared to the amount of time it takes for the spins to recover, then they only get partway there before they find that next 90-degree pulse. And that next 90-degree pulse is going to take the available longitudinal magnetization and convert it to signal. Okay? But the signal's smaller the second time because there wasn't as much magnetization to work with. If I repeat it a third time, what happens, of course, is identical. Because now the time between the pulses is kept the same. Since they start from 0, in the same amount of time, they're going to recover to the same place. Okay? So now we reach a steady state for the signal, which depends on T1. If I have spins which instead have a more rapid T1, then they recover more signal during each TR, and you can see that they then reach a steady state, which is larger in amplitude. So I can see the T1 differences by simply changing the rate at which I apply these 90-degree pulses. These have broad effects on image contrast. Here I'm showing you just the T2 effects, and I didn't mention this. There's a parameter we call TE, and TE, I guess there's a bunch of animations between me and the slide that I would have had this on, so I'm not going to do it. TE, I think as the time following excitation that we collect the signal. So the signal starts off strong, but decays away. And TE is the amount of time we wait between creating the signal and sampling it. Other people call TE the echo time, which is very much a misnomer given the way MRI is currently practiced. But that's okay, you'll call it echo time, everybody will know what you're talking about. Even like I could adopt a new name and you could call me George for the rest of the day, but my name would still be Mark. But we could agree on it, and so that's what's happened with TE. Time following excitation, I think, clarifies it a little bit when we start thinking about how we actually run these scans. Okay, and you can see that which tissues here have the longer T2? Anybody? I'm sorry? Name one. Those are that have the longer TE. Which have the longest T2? Micah, which tissues on this scan have a long T2? Well, I'll tell you that they are the same echo time TE for the top and bottom. I want the name of a tissue. Masa. You don't have to remember. You have to figure it out. The bright ones, right? Because they decay more slowly, okay? So the bright ones, well, here's a name of a bright one. That's called CSF, right? That's water. Water has a wickedly long T2 on the order of 1/5 of a second. Whereas fat has a very, very short T2, and myelin, which is mostly fat, has a very short T2, right? So you get this contrast between the water, the corpus callosum, which is mostly fatty tissue, and the neurons, which are someplace in between, which are mostly aqueous tissue, but they're structured. That make sense? Okay, so you could now think about doing 4 kinds of scans. Two variations might be long and short TR, okay? 2 variations might be long and short TE, and you can combine them all. So you have a little matrix, smallest matrix you'll see in the whole course. And we can separate scans into long and short TR and long and short TE. If the TR is long and the TE is short, what's happening is that with the long TR, the magnetization reaches its equilibrium regardless of your T1. If you wait long enough, everybody gets there. Okay? So you don't see a T1 effect. If the TE is very short, that is, you collect the signal almost instantaneously after it's been created, then the differences in decay rates also don't appear because everybody starts off bright. Okay? And so there are differences. For example, the outside of the head is always dark. And the reason for that are relatively few protons outside the head compared to inside the head. So we call that a proton density weighted scan. If we keep the TR long and therefore minimize T1 effects, but now increase the TE, we see differences in the relaxation rates along the transverse plane. And so those are differences related to the T2, and we call this a T2 weighted scan. The other corner over here, the short TR means the magnetization does not recover completely between excitation pulses, but the amount of recovery depends on T1. So that signal we call T1 weighted. If we keep the TE short, we really don't see the T2 effects. And then we can also acquire these images. But we don't. Anybody want to tell me why not?
Have no signal, right? Because if that's really good. Nobody gets it that quickly, so I should be handing out candy. The signal has very little time to remagnetize because TR is short. But whatever signal you had, you kind of waste away by letting it decay, right? So those images look conventionally like crap. And so, which is why we don't acquire them. Crap is a technical term. It means do not acquire this scan. It's an abbreviation, but I don't know what it stands for. So here are the sort of canonical contrast behaviors of the scan. This is a proton density scan, but it tends to be slightly T2 weighted, or maybe even moderately T2 weighted. And that's because you can't collect the signal instantaneously. And T2s are relatively short, on the order of tens of milliseconds. So that's all the time you have to spend. And so you get some T2 weighting in them. A heavily T2 weighted scan looks like this. Okay? A heavily T1 weighted scan looks like this. Roughly speaking, you can see that the contrasts are inverse between these two quadrants. And the reason for that, if you spend a little time thinking about it, is that T1 and T2 are correlated. If T1 is long, then T2 is long. If T1 is long, T1 weighting tends to make the signals dark. If T2 is long, it tends to make the signals bright. And that is exactly the reason these ones in the lower right corner are called crap, because they lose signal from both processes. Okay? And they also have no contrast, because in fact, because T1 and T2 are correlated, everybody pretty much evens out. Okay, so here's what a good quality data set might look like. These days, we use many, many different variations of pulse sequences in order to collect these images. And the scans of choice for T1 weighted scans are called magnetization prepared rapid acquisition of gradient echoes, or if you happen to run a GE scanner, they're called inversion recovery, forgotten what the SP stands for, gradient recalled echoes. So you could get lots of variations on this. A couple of years ago, we were favoring things called fast spin echo scans. Now on our scanner, we favor a different variation on that, which is called T2 space, but it's essentially the same thing as a fast spin echo scan. And just to follow up your comment with this, what's actually going to happen is you construct these scans out of many, many, many 180-degree pulses, each of which forms an echo, the consequence of which is you can speed up the scan time by collecting all of those echoes with some very odd effects on image contrast. Okay, so just sort of reiterating, but maybe this will clarify it for when you actually try and explain this to your boyfriends or girlfriends. T1 and T2 are kind of different processes. And so on the top, we're showing the longitudinal magnetization, which is dominated by T1. Tissues with long T1, like the blue, recover relatively poorly in between pulses. And the RF pulses are happening every 500 milliseconds in this drawing. Whereas things like the green tissue, which might be fat, recover quickly. After you form a signal from these, they decay away. Now, your first initial conditions, when everybody's fully magnetized, you see the differences in T2 very easily, okay? But here, when you're looking at a partially magnetized state with the RF pulse, what happens is that because the tissues with long T2, what am I drawing over here? Long T2, right, like the blue, tend to have a long T1, whereas tissues with a short T1, like the green, tend to have a short T2, and so you reach this point where they cross. And those are the images with zero contrast. And it's a little bit of fussing around in order to get the right contrast, except that it's an analytic formula. And this is the so-called block equation. Here it is in vector form. But basically, with a conventional spin echo sequence, you can know that the signal intensity is the product of something having to do with how close you are to the signal or how big your amplifier is, something having to do with the proton density, more protons, more signal. You get more signal with a larger magnetic field. That's why we buy these really expensive magnets. And then you have these time dependencies. Here is the T2 effect a simple mono-exponential, and the proportion of the time following excitation to the T2 of the tissue determines how fast these things decay. Okay? And so this is a decay process, but here is the signal regaining, and that's dominated by the proportion of the repetition time and T1. Okay? And so if you know the T1 and the T2 of the tissues, you can go ahead and predict the signal. It also turns out that if you know the signal parameters, you can measure the T1s and T2s. And so if we know the T1s and T2s of the brain, we might be able to predict the best contrast. So here's a little simulation of, let's see, we have TR going this direction and TE going this direction. And the colors represent, and the colors and magnitude represent the difference between white and gray matter whose T1s and T2s are known. Okay, and so it's, whoops, that's another animation that isn't running. That never happens on the Mac. I don't understand. Oh, well. What you could see is that if we were to imagine a line that goes kind of in a curve in the plane of TE and TR, that's a point where there's no contrast. Okay? Over here, when we're looking at long TR and long TE, we have T2 weighted contrast. Over here, where we're looking at short TR and short TE, that's T1 weighted contrast. You can optimize that. This is a nice exercise to do, and it's an important one to do. If you consider, as we will in bold imaging, that we're looking at tiny differences in a T2-like phenomenon known as T2 star, what is the best TE in order to see that difference? And the answer requires a tiny bit of calculus, but it turns out that if you have two TEs, say at 40 and 46, two T2s at 40 and 46 and 6 because of the bold effects, that your best TE is halfway between them. So that's easy, right? So if you really want to optimize contrast for your bold scans, you choose TEs, which are approximately the same as the T2 star of the tissue. So we measure that actually routinely in order to optimize TE and optimize our bold contrast. Okay, as promised, T2 star, what we observe, is made up of multiple components. There is the T2 of the tissue, the molecular processes. And in addition, there's a term related to the magnetic field inhomogeneity, right? That's the dominant term in this equation, and it's called T2 prime. And the observed T2 is actually the sum of the inverse of the observed T2 is actually the sum of the inverses of the different processes that contribute. And in an equation like this, you can certainly imagine whatever is the smallest term here dominates this term. Okay? So because T2 prime, the magnetic field local inhomogeneity stuff, is really rapid, then the observed T2 tends to be close to T2 prime. The spin echo trick removes this effect so that you can see the T2 of the tissues. Okay? All right. And then I mentioned T2D, diffusion, which will be the topic of the afternoon. And so I'll give you some information about diffusion. Okay, so now we've learned about contrast. And this is a primer. You haven't learned everything about contrast, but crucial features for this. So we know how to make a signal. We know that the signal varies with tissue properties T1 and T2, but we don't know where it comes from, other than it must be near my antenna. So how do you make this thing into an image? Okay? Well, there are multiple tricks, each of which revolve around a very, very simple fact, which is that the proton resonance frequency is proportional to the magnetic field. And that constant proportionality, which I showed you before, is gamma, the gyromagnetic ratio, and it's well known. So if I were to make my magnetic field differ along any axis, say it's higher on your right than on your left, what happens is the protons to your right precess faster than the protons to your left. Okay? And so as a consequence, I can spread the frequencies out in a known manner by making a magnetic field that varies with position in a well-known manner. Okay. So starting with, we need 3 axes of resolution in order to make an image. The first axis relies on this magnetic field dispersion, this frequency dispersion with a magnetic field, by taking advantage of the fact that the resonance phenomenon only occurs when your rotating magnetic field is rotating at exactly the same rate as the protons are. So if I have protons over on my left, which are busy spinning at, say, 1,000 times a second, and I apply a rotating magnetic field 100 times a second, these guys won't feel it. It's only when I tune myself up to be exactly at the same frequency as those protons that I get them. So if I make a magnetic field varying from here to here, and say, I'm going to walk over, say that this position is 600 hertz, and I apply a 600 hertz field, then everything in a plane in that section is going to feel my excitation pulse, and nothing else will. So we get a planar excitation, and that's called slice selective excitation. This is Sir Peter Mansfield receiving his Nobel Prize. There are 3 so far that I've talked with you about. Felix Bloch for the magnetic resonance, and Erwin Hahn for the T2, and Sir Peter Mansfield for slice selective excitation. And the idea effectively is that depending on the frequency of my rotating magnetic field process, which is called an RF pulse, which actually stands for radio frequency, that we pick up a different location inside the magnet. And so this is sort of a funny analogy, but the keys on the piano, of course, hit different frequencies. On your left-hand side, low frequencies, and your right-hand side, high frequencies. And if I had a piano in front of me and you closed your eyes, you could pretty much tell where my hands were when I touched the keys, right? It's the same things going on. This is done by setting up magnetic field gradients. A gradient refers to something that varies in space. And here in red, I'm showing what the magnetic field might be in a cross-section of a magnetic resonance imaging system. Okay? And so we make the field vary in an organized manner from one end of the instrument to the other. Unfortunately, we can't make it into a straight line. Because that requires something approximating infinite energy, which we don't do. So it's slightly curved, but fortunately it's curved in a known way. And so you can actually compensate for those curvatures. And of course, over any narrow region, it's linear, because everything is linear to first order. That's a fact. So this is actually done by inserting large spools of wire inside the magnet and then running large amounts of current through those spools of wire. And depending on how densely you've got those wires twisted around each other, you get more or less of a magnetic field locally. And you try and make these fields as linear as you possibly can. But these are huge devices, as you can see in there. They're incredibly heavy, and they involve enormous amounts of energy to run current through these things in order to make it work. They're also the source of the noise in the MR scanner. I usually show slides about this, but I'm trying to kind of advance through that. But if anybody wants to see that, I'll discuss acoustic noise. Now you've got a plane of tissues, all of which is precessing, okay? And it's a plane because you organized it such that you transmitted your RF pulse at a frequency associated with that position. Now let's turn the magnetic field gradient off. Everybody is now precessing at the same rate, and we'll apply a magnetic field gradient in an orthogonal direction, say front to back in here. So now when I observe the signal that comes from that slice of tissue, some of the signal is coming from spins which are in a low magnetic field, and therefore is at a low frequency. And some of the signal is coming from spins at a high magnetic field, and therefore is at a high frequency. The amplitude, of course, depends on how strong the signal was. So sort of going back to our contrast effect, to sort of insert that into your head. Okay, but when I observe it, both those signals are coming in at once, right? How would I detect the frequencies of those signals if they're all coming in at once? Fourier transform, okay? The Fourier transform decomposes a signal into the frequencies that make it up. Just like your ears can listen to multiple notes on the piano at different frequencies, your ears perform a Fourier transform in order to help you do that. If I imagine now a two-dimensional object, or a three-dimensional object from which I've only got a slice, and I have signal coming out from it, and then I impose a gradient in magnetic field horizontally, what happens is that the spins over here might be operating at a lower processing at a lower frequency, or the ones over here might be at a higher frequency. I get back a complex signal, which is the sum of both of those. It tends to look like this. And if I take its Fourier transform, I get this. And effectively, what happens is that this is now organized from low to high frequency. Okay? These guys over here are the low frequency. These guys over here are the high frequency. Oops, the ones at high frequency are of higher amplitude. Why is that? Because something about the contrast in the tissue. Okay? It's a one-dimensional image that I formed. Okay? It's also equivalent, you can think about it, as though I shined a light from here onto a screen over here, right? And I get these shadows, which, by the way, is the way CT works. Okay? It happens to use X-rays for that purpose. Okay, now if instead I had the gradient going vertically, I get all of these signals coming together into this complex-looking pattern whose Fourier transform looks like this, which is basically the shadow from a light over here going through these objects and picked up on a screen over here. Does that make sense? Okay. You could, of course, shine the lights from any angles you wanted, or you could have the gradients going in any orientation you wanted. How many gradients are there in a magnet in order to make sure that I get an infinite number of different orientations? 3, right? Because they're just the vector sum of each of the 3 axes. So I can do whatever I want for the angles here. Oh, there's another Nobel Prize being won by Paul Lauterbur. So Paul Lauterbur figured out that you could do this trick with the gradients and make an image out of it by collecting the shadows in different orientations, by effectively spinning the gradients around the sample. Okay? And so here now is a slightly complex visualization of it. This is now the data as it comes in from, say, my red axis. Okay? It looks like, as I showed you before, something kind of like a sinc function whose Fourier transform is this. Okay? If I projected the signal along the vertical axis, the gold axis, I get this, whose Fourier transform is that. If I run it diagonally, I get this blue curve over here and a different set of shadows. Okay? And I can collect these at a whole bunch of arbitrary angles, and this now becomes the raw data for a complete magnetic resonance image. In order to convert this junk to this, I take the 2D Fourier transform. What's a 2D Fourier transform? I collect a Fourier transform horizontally for each row. And now that I've got them Fourier transformed that way, I then go ahead and do a second Fourier transform along each column. Okay? So it's just doing the Fourier transform twice, but reorganizing the matrix, rotating the matrix. And this becomes the image. Any questions about that? Cool. Okay, that's that. That's how you make images. Now there are other tricks that people use, but that's okay. Doing this is non-instantaneous because I'm collecting the projections along each of these different axes, right? And I have to do them sequentially. Conventionally, what we actually do is collect the data. I'm going to show you this second slide first. We collect the raw data not through these star patterns, because that process turns out to be both inefficient and prone to artifacts. Some people do it. It's called projection reconstruction imaging. Mostly, however, we conventionally acquire the data as a series of lines. Now, it doesn't matter what rate we populate this data space or what order. Its Fourier transform is still the image. And so we collect the data as a series of lines to populate that whole space. The way we collect those series of lines is that we do a slice selective excitation, single slice. Okay? We then pulse a gradient, say, along the vertical axis in here. And what that does is take us from, say, here to here. It's a vertical displacement. Okay? We then go ahead and collect the signal, which happens sort of over in here, in the presence of a horizontal gradient. And here is our signal being collected. Okay? So we've collected one line of data because we've gone from here to here in our raw data space. Okay? Now, collect the next line by pulsing at a slightly different amplitude. We collect a different location in our raw data space, and we get another line. And so we start populating this thing line by line. In between each of these things, there's time elapsing, right? Because each of these lines was acquired with a separate radio frequency pulse. So TR shows up in here. And if I add 256 lines and a TR of 1 second, how long would it take for me to acquire that picture? 256 seconds, 2 minutes and 2 minutes and 40 seconds. Okay, so that's a relatively long time in order to collect an image in this manner, single image. Okay. Fortunately, there are tricks. We saw Sir Peter Mansfield receiving his Nobel Prize. Here's another little Peter Mansfield invention. It's called echoplanar imaging. And Mansfield realized that you could actually, instead of waiting for a TR between each line, rapidly snake through your raw data space in a raster-like pattern and collect all the signal following a single excitation. And that is called echoplanar imaging. It was invented in 1977, but not implemented for many years, because it turns out that this requires that I go rapidly back and forth, which means I have to have enormously high gradient amplitudes, which required a lot of engineering to build. Okay? But that's now how it's done. EPI scans are very interesting because you collect a complete image with every RF pulse. Okay. Question with that? Zip, zip, zip. Okay. So I showed you the idea that you do this slice by slice, but that isn't actually necessary, because I could actually collect my raw data space as a series of planes who are separated now by a gradient encoding along that axis. Okay? And this is now a not uncommon way to collect data. Your so-called MP RAGE scans or your IRSPGR scans are actually acquired in a three-dimensional raw data space. So everything is Fourier encoded when you do this. I don't have time to discuss all of that in here, but I'm happy to discuss it with anybody who wants to know the details, because they're really pretty interesting. And now the imaging time becomes the product, if you're not doing echoplanar scans, becomes the product of the number of planes times the number of lines in each plane times the number of columns in each plane, which tends to be a really, really, really long time, right? And so in practice, in order to do this kind of scans and make them reasonable, TR has to be made very short, okay? Because this number, say it's 256 times 256, that's 65,000 repetitions. If your TR is a second, that's probably longer than you want to wait, right? Even if it's a millisecond, it still has taken time. It's taken 7 seconds. And so these 3D scans typically require a longer amount of time. Now, there are many tricks used for the 3D MP RAGE or SPGR scans. One of the tricks is this multi-echo trick, where you acquire multiple lines following each excitation. All right, there's another way you can speed up the scan time, and that's by taking advantage of what's called multi-slice scanning. One of University of California's greatest inventions by Kaufman and Crooks, however, they didn't patent it, or maybe UCLA didn't get it together. But here's the idea. I can excite a plane of tissue, collect the echo from that plane of tissue, and then, of course, I'm going to do it again TR later. But there's a whole lot of time between the first TR and the second TR. And since my RF pulse affected only one plane of tissue, I could put other RF pulses in there that affect other planes. So this is the way multi-slice interleaved scans are done. I acquire one slice with a RF pulse associated with the frequency of the spins in that location. And then I acquire a different location. And I do that for as many locations as I can get in in the time between my desired excitations of the same slice. So if your TR is long, you can acquire more slices. Probably people have seen that on the console, right? And that's because of the way multi-slice MR is working. Questions there? Okay, so to sort of bind this all together now that we're at 12:30, out of my 84 slides, I'm up to slide 40-something, but that's okay because all the others are intended to be basically advanced topics. I'll do a couple more slides after this. We have the notion of MR pulse sequence, which I've already shown you for the conventional scans. And here the pulse sequence is drawn from the perspective of spatial encoding. However, I can sort of change my emphasis here, and we can see that these time parameters, TR and TE, are also embedded into the pulse sequence. So our contrast parameters are linked to the timing associated with the MR pulse sequence. So they become part of the same reality. I'm going to skip this slide. I do want to show you a couple of diffusion slides before we go. So we're going to go 5 minutes extra in order to do that. There are multiple ways you can take advantage of the motion of things within the magnet. One of them is that if you excite a single plane of tissue which has a blood vessel going through it, and you excite it at a relatively rapid rate, where the TR is short compared to the T1, that plane of tissue will become dark. However, if you have blood flowing into that tissue, the RF pulse associated with the blood the first time is associated with a different bit of blood the second time. So therefore, that bit of blood doesn't see these quick TRs and therefore comes in bright. So you get images which have a bright spot in them wherever the blood is moving. Right? And they look like this. And so here are images with a very, very short TR, and you can see that the blood vessels are exceedingly bright because the blood portion gets replaced in each of these things. So I take all those pictures, and then I look for the brightest dot in any line through that whole stack of pictures, so-called maximum intensity projection, and it looks like that. And these are visualizations of the blood vessels inside the head done with this simple trick. Oh, God. So I'm trying to decide how much of this I want to cover before Van. I want to quickly show you this. If I have spins which, rather than stay in one place, move while we're collecting the signal, then something complex happens during the time that I'm spatially encoding them. Specifically, if I have a gradient pulse which is first turned on negatively and then turned on positively, the spins at the high frequency end of the magnet will spin faster than the ones at the low frequency end, so they'll dephase, right? If I reverse the signs of those gradients, so now the spins that were at the low frequency end are moving at high frequencies, and the ones that were at the high frequencies are moving at low frequencies, then the dephasing will become undone. So the spins will separate their phases over here. This is the ones in the high magnetic field. These are the ones in the low magnetic field. And then I flip the sides of the gradients, and now the phases start to collect again, and we get the signal back. Does that make sense? I hope. What happens if the spins move during that process? Well, you can calculate, and I don't want to do this right now. You can calculate that what happens is for the stationary spins, everything rephases. However, if the spins move with respect to the magnetic field, then flipping the magnetic field around doesn't undo that effect if they continue to move. So the phases now become dispersed. Okay? And that produces, well, I'm going to skip it. That produces a phase dispersion in the scans associated with the velocity. Okay? Van Wadeen, who just walked into the room back in the early to mid 80s, invented a process of vascular imaging based on this phase dispersion here, which turns out to be in every clinical scanner made probably since the mid 80s. and takes advantage of this phase dispersion as a method of angiography. Okay, and those images look like this, and they are one of the more beautiful ways we have of visualizing blood vessels in the brain. So finally, I want to talk about diffusion, and then we'll move on to lunch. So if spins move in the presence of a gradient, they become dephased. Okay? And there are tricks you can do with the gradient pulses to compensate for that, or you could just enjoy the effect and say, if the spins move enough, the signal's going to go away because they all dephase completely. Okay? And you can set up pulse sequences which change the phase not just a little bit in order to see these motions, say, with blood flow, but a whole lot, so that spins, even if they move a tiny amount, end up dephasing. And a tiny amount, say, with diffusion, just spontaneous motion of the spins, even stationary objects, is enough to cause the signal to decay if you use these very large, long gradient pulses. Okay? And the larger and longer those pulses are, the more dephasing you get. And so it turns out, and this is sort of a cool discovery, that depending on the direction in which the gradient is applied, you get different amounts of dephasing, because the spins, if they're all moving in one direction, it's only along that direction they're going to dephase. Right? So if you apply the gradients in this particular case, let me see what I've got on here. Let me show you here. Whoops. In this particular case, the gradients are applied along the x direction, so spins which move left to right become dark. Here they're applied along the y direction, so spins that move back to front are dark. And here in the z direction, so spins that move through the plane are dark. And these images are very obviously different. Right? And it didn't take much of a neuroscientist to recognize that the principal thing that you're going to see here is the direction of the principal fiber tracts in the brain. Right? You can see the corpus callosum. Let me see if I can. I can't really see from this axis. The corpus callosum is exceedingly dark when you have the gradients on horizontally, whereas it's brighter when the gradients are on. Oh God. Can't even see it over here, right? It's brighter when the gradients are on through the z direction, because the corpus callosum is going left to right in that plane. From this, it's possible to infer fiber orientations. And the reason that's understood to account for this, or at least is accepted to account for that, is that if we now take a myelinated fiber, and I showed you myelinated fibers on Monday, which are, remember, aqueous tubes surrounded by fat. The water doesn't go out through the fat very much, so the spins presumably are restricted from moving outside of the fiber. So if I were to go ahead and take a random diffusion of spins in these fibers, you'd see that they tend not to leave the myelin sheath. On the other hand, if I have the thing, here's my cursor, I guess. If I have the myelin fiber viewed in the orthogonal direction along it, you can find that the spins move more in that direction. Okay? So viewed, if the gradients were going top to bottom on here, what you'd find is that the signal becomes very dark along the direction of the fibers. Okay? Because the spins have moved a lot along that direction. Okay, so that's all I want to say before lunchtime. I'll stick around for a couple minutes of questions, and those of you who want to leave for lunch, go ahead. Any questions? Yeah, cheers.
right, close enough. Technology is really great when it's an obedient servant, and otherwise it can have completely perverse effects. Just watch Dr. Strangelove. Go ahead, introduce me. Hi, I'm Van.
Hi, it's a great pleasure for me to introduce you to Van Wedeen. Van Wedeen is one of the most important scientists operating in the field of MRI. He's made incredible discoveries, going from, as I mentioned, flow imaging, Fourier imaging of various kinds, diffusion imaging, many, many major contributions to the field. Van, for the past couple of decades, has been concentrating his efforts on trying to understand the architecture, the physical architecture of the human brain. And he's a many times speaker at the NITP, and I don't do elaborate introductions because it cuts into the time, but I know we're going to enjoy Van's talk.
Thanks, Mark. Let's see, I guess I would like to go over to I just pulled the plug on this thing to get, but that didn't work. I wanted to use the projector, the whiteboard. So mostly you're here to talk, to learn about functional MRI. And as Mark and I were discussing last night, fMRI has become an extremely mature technology. And one of the interesting definitions of a successful science is that it knows what its limitations are. So if you think about Newtonian physics, for example, not only does it make predictions that you like to have, but you also know exactly where it burns out. You know the limits. You know there's a small scale limit, quantum, high speed limit, special relativity, big heavy limit, general relativity, yada yada yada. And then of course there were some limits that came as a big surprise. Look at the way we oversold Newtonian mechanics with respect to chaos, right? In the 18th century they were saying, you just start with the initial conditions and you predict everything. And it's like, yeah, well, oops, it turns out when you get to a three-body problem, you're hosed. That's not going to work anymore. So we don't even know if the solar system is stable in 500 million years. Well, so fMRI is a mature field in the sense that we kind of know a lot about what it does and how it works and when it stops working. Now, the other thing it has going for it is that it's functional. What that means is you have you're looking for just a change. You're not looking at the raw signal underlying the process. You're looking for a change. Those angiograms that Mark showed are the earliest example, I think, of functional imaging. It was a difference of blood flow, no blood flow. And that's kind of what you're doing, in a way. You're looking at a change in flow. Now, diffusion imaging is not a mature field. It is anything but a mature field. We have some mature buttons we can push, but as to what diffusion it is, and it is immature in two extremely radical senses of the word. One, we don't know what we're measuring. That's bad. But there's actually something a lot worse, and that is that we don't know what we're looking at. We don't know what the shape is of the brain, nor do we have any clue on the relevant scales. So let me explain what it would be like to not be clueless and convince you that, in fact, we are profoundly clueless. Let's ask the question, so has everybody here had a human anatomy, had an anatomy class at some point? Can everybody think of some organs in the body that are well-defined and other organs in the body that are not well-defined? Can you name a well-defined organ? Let's start easy. What's an organ with a very good definition of are you in it or not in it? Kidney, wonderful. Heart, a little less so. It's got these vessels that are kind of stuck to it, so where does it? The kidney is pretty good. The heart's decent. What else you got? You don't break out in hearts. Are there organs that you can break out in? What? Well, spleens. You can certainly have spleens coming up everywhere, but a spleen is pretty well defined. But that's a good step toward name an organ that's totally ill-defined. What? Skin? Well, I don't know. I mean, you kind of got a two-dimensional surface. I was wondering about the skin. It's pretty well defined. The gut is a tube, but it's got segments. Hard to say. No, the one I had in mind was bone marrow. How do you know, the hematopoietic organ of bone marrow? Is there such a thing as saying, are you or are you not in bone marrow? No. It doesn't have anything like a boundary, okay? There's a lot of, the connective tissue organs tend to be like that. Now, when did we learn that organs have boundaries? So our conviction that we know anatomy when we know the organs and that organs have well-defined existence and boundaries, when was that clear? Well, it was certainly clear in the Iliad where they're hacking people in half. All you got to do is hack somebody, cut somebody in two, and then you see the parts fall out, viscera. And it's convincing that there are parts. Now, with respect to the pathways of the brain, have we had the moment that looks like the Iliad? Have we ever held a brain connection in our hands? Can anybody think of something that is like a connection that we've held in our hands? Well, when you look at peripheral nerves, or things like the optic nerve, they look pretty much like a classical wire, okay? So you cut your radial nerve, your hand goes numb. Okay, so it's fairly convincing. Or an optic nerve lesion, right? MS, boom, no eyesight. Okay, but then when you start getting into the brain, and by the way, are these things running around? I don't know about peripheral nerves. Well, every peripheral nerve is, motor and sensation. And as you know, sensation has multiple modes to it, right? So it's already, when people say the word pathway, it turns out that different people are talking about completely different things. So when you talk to a radiologist about a pathway, or a surgeon, they mean a location in the brain through which a lot of fibers go. When you talk to a neuroscientist about a pathway, what they mean is a collection of axons that have cell bodies in one location and that then go to multiple other locations. So they're talking about the cellular counterpart. And when you talk to a neurologist, they'll be back and forth between those things depending upon what their context is. Are they talking about an upper motor neuron lesion like ALS, or are they talking about a clock on the head and traumatic brain injury and what the localization might be for TBI? So, but when you try to look inside the brain and you say, are there pathways? Well, there's some pathway-like things. You certainly have a spinal cord. That might be like a pathway. You have a corpus callosum. You know that these things contain zillions of different, not just architecturally distinct, so it isn't just the trivial distinction of, let's say, the internal capsule, where you go from foot to hand to mouth to viscera, topographically. It's that you have completely different modalities going in multiple different directions in the same anatomic hunk of stuff, right? But the real question is, has anybody ever seen a pathway of the brain? So we say there are these connections. Who here believes in Brodmann areas? And how much do you believe in Brodmann areas? Because you can give it a scale, do you believe in them from -5 to +5? And I think the answer is, it depends on your field. If you're doing vision, you have very good reason to believe in V1 and pretty good reason to believe in V2 and V3 and something, and MT. If you're doing attention, do you believe in the frontal areas? You know the answer to this, of course. You know that these things are statistically defined. Their definition is not absolute. They're not like the kidney. I don't know, does that make them like the bone marrow? They certainly don't have sharp boundaries, that's for sure. At least not all of them. Some may. Maybe there is a V1, V2 boundary. Maybe there really is a fairly sharp S1, S2 boundary. Those are the exceptional cases. Most of them are not like that. The trouble with saying anything is that the unreasonable effectiveness of mathematics in physics, that whole line of reasoning, and then there were subsequent papers that said the unreasonable ineffectiveness of mathematics in biology. It's very hard to make generalizations in biology for which counterexamples don't come readily to mind. The question is, are there pathways? Has anybody ever seen one? Well, the evidence of pathways, the answer is sort of yes and sort of no, and it depends on who you ask and who you look. You gotta ask for what is the hard data upon which people base their beliefs. You can't just take their word for it. You've got to say on what are they basing, what is the evidence? So the evidence for fiber pathways of the brain, on the one hand, you have the appearance of the brain. You tear it apart like a cauliflower, and sometimes you perceive linear structure running in a preferential direction. And that linear structure is represented in the diffusion images, such as the ones that Mark has just shown you. That's one kind of evidence. Then you talk to, let's say, David Van Essen and Henry Kennedy. Now, they will get a team of rhesus monkeys and inject cortical areas, and they will then report the statistics of the connectivity of cortical areas. Now, when they say that they've put tracer into one cortical area and that tracer has appeared in another cortical area, well, that's a fact. That this area was definitely connected to this area by neurons which had certain transport characteristics that moved that tracer. There had to be a cellular connection from area 1 to area 2. So the connection did exist. We got that. But then the question comes in, how did it get there? Do we know, how much do we know about how it got there? And what is the nature of our knowing of how it got there? Well, that's where things get really dicey. So you put the tracer in over here, and it comes out in 5 other places. And once in a rare while, somebody will take all the slices of the brain and try to make a cloud or map of how the tracer got there. Now, should you be satisfied with that result? Again, it depends what you're doing. Let me see. How do I get to this? Mark introduced the concept of diffusion, and our hypothesis is going to be maybe we could figure out, so why are we having this conversation, you and I, today? It's because we have a hypothesis, maybe we could figure out the connectivity of the brain using a non-invasive tool, diffusion imaging. Wouldn't it be fantastic if we could map connectomes in a widely available modality that can be used for a few $100? Now, the question is, what structural scales, Mark didn't have a chance to go into this, what structural scales is diffusion sensitive to? So when you map, you get the general gist of it. We can talk some more details, and that's why hence the whiteboard. When you do a diffusion image, how far the water molecule, you got the idea that water makes a kind of fuzzy picture of the shape to which it has access. We can call that shape the container. That coinage is due to David Corey. And he said, well, it resembles the autocorrelation of the container. Who knows what an autocorrelation is? Anybody? Yeah, some, half? Okay, the autocorrelation of the container. So it's a very, very blurry image of the container. Okay, what scale is that happening? Okay, it's happening on the scale of, the diffusing water molecules, let's say, are, how far does water diffuse within an MRI experiment, within a coherence time of a spin? Typically, that's TE, and typically that will be 50 milliseconds, under 100 milliseconds. You can make it up to a second if you want to use stimulated echoes, but it's a small fraction of a second. And so the scale is under 50 microns, let's say, maybe under 20 microns. So our diffusion is a probe of the shape of the tissue on a scale, on a very small scale, on a scale of, let's call it 20 microns, give or take. Now, is there a minimum scale? So in other words, anything happening beyond 100 microns, diffusion can't reflect it because there just hasn't been enough time for a proton to travel 100 microns or 200 microns. So it's all just this very small scale. How low does that scale go? What is the smallest scale to that diffusion might reflect? Well, there is no lower limit. Diffusion, the diffusion of the water might be hindered by little molecules that it's bouncing off of next to the next water molecule. So, do we have any examples of that? Yeah, diffusion in muscle. Diffusion in muscle is mostly water interacting not with membranes, but with proteins. And so you got these the muscle is full of fibrous proteins, and the water is bouncing off the proteins. So there really is no lower limit. So when we ask the question, do we know the shape of a fiber pathway of the brain? What can we say? Well, we can say we've never held one in our hand, we've never isolated one, we've never dissected one. Do we know if pathways have boundaries like the kidney or indistinct boundaries like the bone marrow? No, we don't know that. Could we know that? I challenge you to see what kinds of information there would be about the path of a single axon. There will be studies of single axons or few axons. Either you got a study that shows our 5 favored axons, or you have a study that shows the aggregate tracer uptake due to millions of axons. And in that gap, that's where diffusion imaging lives. It's looking for the average effect of all of the little 10-micron structures. So to know what diffusion is doing, you've got to have a census of all the structure, 10 microns and smaller, throughout the volume that you're looking. Wouldn't you? Don't you agree that you would like to have that census in order to be able to know with confidence what the diffusion is talking about? Agreed? You would need to have that census if you wanted to interpret the diffusion data. Has anybody produced such a census? Is there a form of imaging, a modality of microscopy, that would today be capable of providing a census of that kind? Any takers? You got one? I'll tell you a couple that you will hear, that people will tell, the snake oil salesman will tell you. They say, well, we can do it with electron microscopy. And it's like, okay, how many exabytes are we talking about? You're saying we're going to just sample the brain down to 200 nanometers. So we're going to make the 200 nanometer voxels and add them all up. So you're getting petabytes per cubic millimeter. That is, not doable. And Jeff Lichtman is out there building 100-channel electron microscopes. It's doable in principle, and I wish them the best, and I'd love to see the results. But it's they're stuck with the problem of tiny sampling. They have a real sampling problem. And so they can't talk about a primate brain as a whole object. They can talk about a cubic millimeter of a mouse brain very nicely. But as to a connection, a large-scale connection in a primate brain, I see Moore's law slowing down. Don't hold your breath. Okay, another contender, polarized light microscopy, basically has technical limitations. So basically it's not exactly three-dimensional, and basically it only produces one direction per point, and that's fatal. So it doesn't exist. Short answer, it doesn't exist. So why am I going on this long story about what we don't know? It's because a minute ago we addressed the question of recognition. The question was, how do you recognize an organ when it's presented to you? And we talked about the iliad and the gut spilling out. You can recognize, frankly, we recognize organs because they have surfaces. And if you didn't know whether CAT scanning worked or not, you would say, oh, I do a CAT scan or an MRI scan, and I see these surfaces. And you would know right away that it was telling you the truth, because a random structure wouldn't produce surfaces, whereas the CAT scan is showing you that the kidney has a surface and the liver has a surface. So it is this discrete character of the underlying structure that convinces you that the CAT scan or the MRI scan is inherently real, if you didn't know before. Now, so we are now faced with basically the same. So when I say diffusion imaging is not mature, and I said there were two senses, what would it take to convince us that diffusion imaging was working the way it should, was telling us anything real? Well, if we saw something like a discrete structure, if we saw something that was that couldn't be put there by accident, then we would have to be convinced that the diffusion imaging was showing us something real. Okay? So, for example, like the surface of a kidney. you could go one step further. Let me give you a further version of that that might make you feel a little more comfortable. A related feature of the kidney is that it doesn't change very much when you improve the resolution. If you took an image of the kidney, that surface wouldn't change as you build a better camera with higher resolution. Now, other things might. I'll give you a case in point, a more relevant example than the bone marrow. What's the example that's like the bone marrow in pathology? Cancer. What is the boundary of the tumor? Does the tumor have a volume? This comes on again and again. There are certain kinds of lesions that have well-defined margins whose volume quantitation is robust. MS probably. Some cancers, especially benign ones, but aggressive cancers, tumors don't actually have well-defined boundaries. The pathologist will sit there and argue. Consequently, attempting to quantify it is not a simple anatomic question. I see you nodding your head. Yes, you might be able to get a marker that's proportional to the volume, but that's not the same as saying you found a boundary or established where it is and where it is not, because that question, is fundamentally metaphysical in the sense that what defines a cancer cell, given that a cancer is heterogeneous and so on. But we have the same question. So, excuse me, I'm not getting a cold, I'm getting over a cold. So the question was, what would it take, does diffusion MRI, is diffusion MRI capable of producing evidence of structure that we did not previously know existed? So that really is the question. And that's the sense in which this is not a mature technology. We are changing, we keep changing diffusion imaging. We have many different methods for doing it. And we're looking in the dark for evidence of a structure that in a sense won't go away. A structure like the surface of a kidney, for example, that that is well-defined and that doesn't shift or change when the parameters of the imaging are changed, and especially when they're improved. Now, I would draw your attention to a paper by Carlo Pierpaoli in PNAS about a year and a half ago. And in this paper, he said, do we get the same answers if we make a map of, okay, let's go back. MRI is not a tracer, is there an MRI method like a tracer injection for connectivity? Yeah, manganese. You can put in heavy metals. That's the Alan Koretsky experiments. You can put tracers in that are MRI visible and track them around the rat. Are you going to do hundreds of tracer injections in a single unfortunate volunteer? Not in America anytime, at least for 6 months. Okay, we got that. But the hypothesis of diffusion MRI is that you can tell the connections by looking at what's in between. You're going to look at the tissue and you're going to try to infer the connections. So, as Carlo said, that doesn't have that property of stability. That when you compare the connections that you infer from diffusion MRI with the real connections that you got by putting in tracer here and watching it pop out there, are the two things concordant or discordant? The answer is not very concordant, and getting better images doesn't necessarily make things more accurate. That, in a sense, was the really disturbing feature of his paper. It's that you do better imaging, and instead of getting a more accurate result, some things get better, some things get worse. Now that's the worst case scenario. So with all this said, I want to interest you, in a sense, in the fact that we have an anatomic puzzle over which we have insufficient leverage. We have not seen what pathways look like in passing. We know they exist. They are predictable because you pump in stuff here and it comes out there time and time again. And frequently it goes by something in between. But there's still a descriptive gap that we with MRI do not yet know how to cross. So we are, therefore, what's the word? The whole question is open. It's anybody's game. We don't know what the underlying anatomy really is because we've never seen it. So what does that mean? That means write your congressman and get them to fund people with better microscopes. Get them to fund these electron microscopes and let them do the best they can. But second of all, we have to try to understand what we can and can't do with MRI. Now so here's what I'd like to do. I'd like to show you a few pictures about just how odd the brain may in fact be. I'm afraid I'm going to have to blow your mind concerning what the brain is like. Secondly, I'd like to talk a little bit about how diffusion imaging works, so that you can be kind of up to speed on these technologies and buzzwords that you'll hear about all the time. Now, let's see. There should be a button here. Does that work? I wanted to show you this. Back to the heart. So, why the interest in diffusion? I want to go way, way back. If you look at T1 and you'd say, is T1 a biological parameter? The answer is definitely not. The body doesn't know what its T1 is. It doesn't have T1 detectors of any kind. Now, how about perfusion or deoxyhemoglobin concentration? Well, that's absolutely a biological variable. The cells know what their local oxygen concentration is. They care a lot, and they got all this machinery to keep it within a target range. Now, what's the status of diffusion? What is diffusion really about? Well, the reason I was interested in it initially was that I figured diffusion was part of the signaling process by which the body creates itself, that all the markers, all the message molecules, the shaping of all biological tissue must be at some point based on diffusion. You have diffusible markers and diffusible tracers. Of course, it's equally true that perfusion is really just a refined version of diffusion. So diffusion is really is as basic a biological process as you can think of. If you don't believe it, just try cooling your body temperature to 80 degrees and tell us what it was like. So anyhow, just as a little example, this is an MRI tractography of a rat heart. Okay. Now this is actually the direction. How tractography works. You map the direction of the diffusion, and then you connect the dots. Okay. Is that all familiar to everybody? You've seen the images everywhere, and you kind of get the gist. But this isn't a made-up picture. This isn't smooth or simplified. The surface of the heart turned out to be, what the surface of the heart is like. It looks kind of weird and ugly, and it doesn't make a lot of sense. You hold a heart in your hand, and until you know some things about it, it looks nonsensical, I would say. Fair statement. Your first reaction to a heart when you see a plastic model of a heart with all these funny little parts. And when you look at the surface, the outside or the inside, again, it looks very arbitrary. The distribution of the coronary arteries certainly looks arbitrary. It looks like a random tree, and then you open it up, and you have these trabeculae and papillary muscles, and again, it looks very ad hoc. But the muscle architecture of the heart is something incredibly simple. And so once you look beyond the surface of the heart, using this diffusion camera to see the architecture inside, the eloquence of this mechanical solution, this particular sort of double helix arrangement of muscle is effectively a unique engineering solution to the problem of what the heart's supposed to do. And I'd love to talk with you later about how that comes about. But really, this is the unique heart in the universe, given muscle fibers that want to contract 12%, and given that you want a factor of 5 dynamic range between rest and peak exercise. So if you have those two facts, this thing is specified. Second of all, this is one of my favorite shapes in the mathematical universe. It happens to be a thing called SU2. It's also the unit quaternions. This is the roundest and most symmetrical. If you got a bunch of particle physicists in the room, they would agree that this is the roundest and most symmetrical object in the universe. It's much rounder than a two-dimensional sphere. And so it's just kind of funny how the heart solution converged on this uniquely symmetric mathematical solution. It's a little subtler than this, but to a first cut. So this makes you really feel hunger for understanding the brain. You say, you look at the brain, and boy, does it look weird and ugly on the outside. And you're looking at it and saying, this is the weirdest thing I've ever seen. There's nothing about this shape. I don't know which end to look at. I don't know how to see it. And it looks completely arbitrary. This was disturbing. It's not necessarily the case that just because it's disturbing, that means it isn't the case. It was, however, disturbing and somewhat unsatisfying that something so important should not express what it's doing in any intelligible way at a large scale. Now, of course, all this requires a considerable leap of faith that the scale of description that we're discussing is actually salient to what the brain does. Now, some people would argue, oh, maybe it isn't. Maybe it's all just little local wires or random stuff, so that looking at it at from this macroscopic lens, architecturally is just a non sequitur. It has nothing to do with the brain, as it has nothing to do with the maybe it's like the bone marrow. But it could be something different. Open question. So the version of the brain that we have been presented by MRI, is this. We have this fiber architecture that comes from diffusion. This kind of fiber architecture represents multiple levels of technology. So the early technology for doing this was diffusion tensor imaging. The tensors, as Mark pointed out in 1995, after we got the first tensor images, well, he just looked at them and said, well, they're very pretty, obviously unrealistic, because obviously you have different fibers crossing at a point. It's critical. You could never build a brain if you didn't have fibers crisscrossing. Now, some people's reaction to that was, well, you just need higher spatial resolution. They just cross like all those sewer pipes underneath Manhattan, and even though they're all crossing underneath 6th Avenue and 48th Street, they're actually at different levels, different depths, and if you just had a fine enough map, you could sort them all out. So you should just get higher resolution and try to sort the matter out. That was one response. The other response was high angular resolution diffusion imaging, which you may have heard of. DSI, Q-ball, Hardy, all these high resolution things, which can pick out more than one direction per point. It's basically just a sharper image. Now, so this was the version of the brain that we were being presented with diffusion imaging. Lots of fibers, very complicated and confusing, no particular aha moment. And then a connectivity map that comes from counting the density of solutions between pairs of ROIs. So the two technological steps in this thing, one, I know a lot of you are interested in technology and what technologies are needed. Technological step one is high angular resolution. Technical step two is a magnet capable of doing high angular resolution. And what that primarily means is powerful gradients. It primarily means not more Teslas, not 7T, that's such a nice thing for functional bold imaging, but rather the gradient strength. Everybody know what a gradient is, right? What? You just talked about it. Exactly, those things. That's the thing that makes the clicking sound. And there are two problems with building there are a bunch of problems with building a powerful gradient. One is that it wants to squirt out of the magnet like a watermelon seed, hence the noise. The other is that it wants to melt. So you want to pump as much electricity as possible into a very small bundle of copper, and you've just got to cool it, basically. So you've got to have, thousands of volts and thousands of amps mixed with water. But that's just, that's just like what you're doing. What was interesting about it, so we built this connectome scanner at MGH. I don't know if you may have heard of that thing. The key ingredient, really, was to realize that gradients were not being engineered out to their limit. That people knew what happened when you tried to build more and more Teslas into a magnet. You get a heavier and heavier magnet, and certain changes ensue. But gradient strength had not really been leaned on, and so we leaned on it as hard as possible. and got a gradient that was 10 times stronger than the gradients that were running back in 5 years ago when this all happened. And the result was far, far sharper diffusion images with finer resolution. Anyway, the question is, do you believe this? Is this view convincing? Is this the bone marrow case? I mean, is this the bone marrow case, the kidney case, or can't tell? Is it that we have no real way of knowing because of Carlo Pierpoli's point that it keeps changing, that if you just did this image with a new system, what makes this the right answer? Is it just this is the best we could do this week? Just saying that we got it again and again doesn't really address the question of reality. Yes, it's better than the canals of Mars because the canals of Mars keep changing from day to day or telescope to telescope. But here, if we just say this is the strongest scanner we can build, is it proof by exhaustion? Is that where we want to leave this? So here's what I'd like to show you. Let's discuss for a minute the corticospinal tract. Now, the corticospinal tract, I think you'll agree, is one of the most talked about and basic entities in the brain. It's, right? I mean, everybody kind of believes it's there. It is there. So we're talking about the output from the primary motor cortex that runs through the internal capsule and then goes to the spinal cord. Now, and these are the pictures of the corticospinal tract that have been drawn. Well, this is the 100-year-old picture. No, this isn't 100 years old, but Desjardins had pictures similar to this. This is a picture from the Connectome project. Actually, this is done from Toga's lab when he was here at UCLA. I guess I can't even remember whose data it was. The point is we have a picture of the corticospinal tract as a smooth structure. And why not? I mean, when you do a tracer injection in a monkey, it kind of goes this way. Okay, right? So this is a very classic example. Let me see, I don't even know what slides I have. Okay, I'd like to show you this image for your amusement. And I'd like you to pay close attention. So this is a tracer injection in a rhesus macaque. So Doug Rosine and Farzad Morzavi got a rhesus macaque, and they squirted the dye in, by a method they've used 100 times. You can look at the average intensity of the tracer in this region. Do you see it? It's faint, but you see this average intensity. And so if somebody said, the average intensity seems reasonably consistent with the picture of the tracer injection, with the picture of the classical corticospinal tract. It's kind of going from here. So this is, do you understand this experiment? Biotintylated dextranamine is injected into the cortex, has uptake by the pyramidal axons, and is transported anterograde down the motor projection axons wherever they go. So if they go, some of them go to the spinal cord, some of them go to association areas, some of them go callosally, some on the way south, they make branches. They'll make a branch to the striate, they'll make another branch to the thalamus, they'll make pontine nuclear branches, but it just carries the stuff, right? Okay, now let's go to higher magnification, because we're asking the question, what would the diffusion show us? We're asking the question, what is the nature of the inference of this structure from the diffusion? Let me go back a little bit. I'm going the wrong way completely. Okay, so what you're trying to, no, too far. Yeah, you're trying to say, okay, we believe these red lines because we know it gets from here to here. Let's assume let's say that's what these red lines represent. They don't represent really the path so much, but they say it got from here to here. And the diffusion looks like it's showing the same thing. But how is the diffusion built? It's interrogating every little cube, every voxel along the path, and asking at every voxel, what are the fiber orientations in that voxel? And now we have to say, are the fiber orientations a legitimate guide to how the thing is connected? And you would say, how could they possibly not be? It's like saying, is the trajectory of a ball, is the velocity of a ball a predictor of where the ball is flying? Well, balls have one kind of physics. They're governed by Newton's laws. And balls only change direction when a force acts on them. Do we know that about axons? Are axons inertial? Do they have Or perhaps they have a minimum path length law, as David Van Essen suggested, that they're like little rubber bands that want to be as short as possible. Why not? Other things being equal, they might want to be as short as possible. But have we proven that? What is the evidence that that is the case? So here's the picture I would like you to go back and look at. This is high resolution of this area. And we should be seeing arcs of axons sweeping through from upper left to bottom, from 10 o'clock to 6 or 7 o'clock. Agreed? Do we? What do we see? You see the tracer uptake axons in this field. So the pink are cell bodies. What are these cells? So we're in the middle of white matter here. What are these cell bodies in the middle of white matter? Mostly they're glia. There also are a few neurons in white matter, cell bodies of neuronal cells. So the axons that were injected here are now black. What are their orientations? Please only tell the truth. Don't lie, because that's the right answer. What? Yeah, they're going in two directions only. They're only in two axes. They're horizontal like this, and they're sheared like this, and sometimes we actually catch them making branches between these two directions. Now, do we agree that axon branching happens? Does everybody agree that axon branching is a real phenomenon? Yeah. Does everybody agree that axon branching is a real phenomenon under genomic control? That that's an actual popular mechanism of axonal navigation? You should go look at a book on axonal navigation, and what you'll see is that axons will frequently creep along until it's time to stop, and then they'll throw off a collateral branch. And then both pieces will propagate, and then one will connect where it's desired, and the other half will die back. And it might be and so frequently, for example, in the spinal cord, you see this. Something grows in, grows down, sends off branch, 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 and then one of the branches hits its target in passing, and then the thing going forward just dies back, and so you're left with a turn. Sometimes they both survive. So what do we see? We don't see arcs. What we see are two axes. So this, there's no other polite way to say it. This is the oh shit moment. These things are not swerving around in smooth arcs. They appear to be tracking along two discrete axes. Now, by the way, this is just confocal. This is a high res of this guy, and this is confocal imaging. And what this actually shows is multiple things turning at right angles. This one is actually turning at a right angle in the third axis. It actually comes out like this, then comes forward a little bit, and then it goes the other way. So, how could this possibly be the case? Well, I guess maybe I'll go to this slide later. Here's the thing that's going to blow your mind. The brain's a cube. So when you look at every living central nervous system, anything that is alive on planet Earth that is a central nervous system is orthogonal. There are no exceptions. Sorry. So if you want something that isn't orthogonal, you gotta. I'm not entirely sure what the status is of things like jellyfish and hydra. They don't have centralized nervous systems. So when you see the nerve net of a hydra and think that's a counterexample, I've got a little weasel word in there that protects me from that counterexample. I'm saying centralized nervous system, not nervous system. So if the nervous system is centralized, then it's orthogonal. I think that's a correct result. Now, how can you be so flat-footed about it? Well, if you look at the evolutionary tree of eumetazoa, the most basal animal we can imagine on this tree approximately is this thing, is approximately an acelomate or worm, which is a member of the, it is a sister group to all of the other bilateral animals. So all the bilateral animals are divided. Basically, you got the insects and squids and everything. You got deuterostomes, who are the ones like us, the chordates, and you have protostomes. The protostomes are the one where the nerve cord and the mouth are on the same side of the body. So that's true for ants and scallops and octopuses. All those creatures have nerves, have a nerve cord and mouth on the same side, and they're bilateral. We have a mouth on the wrong side, so our nerve cord is on one side and our mouth is on the opposite side. And how did that happen? It swiveled 180 degrees in one of our ancestors, possibly because the ancestor, and we know whether it was left or right, because we have embryonic forms of some animal in between where you can see the thing moving around. It's probable that what it was doing was eating sand and dropping the sand out of its gill sideways, hence the advantage of a sideways mouth and a vertical gill. But whatever the actual story is of how this rotation occurred, so that's this branch, and then the sister group to all of those bilateral animals. This worm doesn't even have a through gut. This worm's gut has a single orifice in the center, and the gut is simply a bag. And the food goes in, gets digested, and comes back out. So it doesn't even have an axial gut yet. And yet its nervous system is bilateral, is orthogonal. It has longitudinal nerve cords and horizontal nerve cords like a checkerboard. This is our big friend C. elegans. C. elegans has a cylindrical nervous system. I think it's got 4 nerve cords running longitudinally and multiple rungs running transversely, and I don't know, 24 groups of muscles in, I'm trying to remember the numbers. They're like groups of 4 in the 4 quadrants, conspicuously orthogonal. And then this is a flat map of a mouse by Larry Swanson. And in this flat map, well, of course, you see in the spinal cord the conspicuous orthogonal organization, which probably wouldn't surprise anybody. He basically doesn't suggest whether there is an orthogonal organization in the forebrain. And the short answer is yes. And actually, there's a whole literature on this subject. So let me see. Oh yes. So here's another nice picture. So the genomics of this. It's a case of duh. You know the Hox system is present in both protostomes and deuterostomes. It's the system that causes segmentation from nose to tail. And then you have a front to back gradient. So you have the sonic hedgehog and bump genes creating a rostrocaudal gradient, which gets kind of mixed up because we start out kind of flat and then the thing folds around the front. But so you can call it proximal distal, but you got to remember distal is the midline in the front. And if you remember the distal is the midline in the front, then it's proximal to distal, it's lateral. In any event, the 2 axes are already written in the genomic architecture and preserved in the histological structure of this is Louis Puel's model of the segments of a brain, sort of trying to say, if we carry forward the columnar and transverse structure of the spinal cord and midbrain, the spinal cord into the midbrain, the diencephalon, and the forebrain, does it work? Yes, it does. Long before Puels did this, Rudolf Neuenhuis already knew, Rudolf Neuenhuis has his work from '77, I believe, in the lamprey, which is a jawless fish. So its forebrain is kind of coming along. Its forebrain is very much of a work in progress. But what's interesting about this is that he's noting that the directions of the fibers are indeed parallel and perpendicular to these genomic zones. So it isn't just that you have a map of histological areas, it's that the map of histological areas is that the white matter is tracking along this map. So it's basically holding position with respect to an implicit coordinate system. And I'll say that Nieuwenhuis is very much aware, has basically called this sort of a Darcy-Thompson approach to the architecture and connectivity of the brain. So this concept of a brain with cubic symmetry or with orthogonal symmetry in 3 axes actually turns out to be quite well known, but not exactly applied in our universe. We had sort of assumed that the structures that we were looking at were exempt, or if not exempt, then perhaps it was just a problem of recognition. We couldn't see how such a structure as this might yet be materialized in the architecture of the forebrain. So back to the, in fact, once you start to understand what's going on, this, I'll just show you, is, wrong direction. This one you'll know real well. This is no exception. You all know that the cerebellum has got a cubic architecture. The question is it the same cubic architecture? Probably. You know what I'm referring to. That you have 3 mutually orthogonal axes, the input-output axis, perpendicular to the cortex, but then you have the cortex consisting of ththese parallel fibers running left to right, and Purkinje arbors shaped like discs, like poker chips, running vertically in the sagittal plane, rotated away. Now, I began this with a discussion of what does the corticospinal tract probably, I'm going completely in the wrong direction. What does the corticospinal tract probably look like? Well, here's, wrong one, here we go. Here's what better MR shows in the corticospinal tract. So it doesn't show fibers curving up. What it shows is things crossing. Now, it doesn't, so here the cortex is over on the right, over on the far side. This is the callosum over here. And we don't actually see the turns. Well, of course we don't see the turns. The turns are too small to resolve. The turns do not produce any orientation effect in the diffusion. Let's go forward. Imagine measuring the average orientation of the axons in a chunk of tissue like this. Okay? You would have some orientation this way, some orientation this way, but you would never catch one in the act of turning because the actual turning zone was 1/100th or 1/1000th of the size of everything else. The turn is just an axonal connection where an axon has come in and branched. It's just this physical branch and nothing more. So of course, there are no intermediate angles. There's just, what there might be is relatively, it could be that the stuff comes across and gets depleted as it comes across and materializes in the downward direction. So this is what the corticospinal tract looks like in just really good diffusion MRI in a rhesus monkey brain. And really good means 3 things. It means lots of signal to noise. It means very high resolution for diffusion, so you can pick out all the little details in the diffusion signal. And it means, and here's the thing that everybody frankly gets wrong, the tissue for some reason has to be very fresh. The tissue dehydrates over the course of a week. And so you've basically got to get the brain, pop it out of the monkey, and move it into the scanner within a few days, a week at the most. But if you're out at 2 weeks, things are getting very challenging. By the way, I would pay serious money if somebody could solve that problem. Tell me, just add, sucrose, and the thing puffs back up, and you can take brains off the shelf that have been sitting in formaldehyde, since Deepak Pandya injected them in 1949, and you can image them. It's like, thank you. Just, we'll set up an assembly line. So in any case, this was the configuration. And so the hypothesis is that axons may navigate through the forebrain using a discrete code, using a code of 3 axes, left, right, top, bottom, front, back. Whether it's a code or not, or whether it's more like Darwinian. By the way, I just want to point out one more thing. I mean, believing this image is sort of the key to this whole discussion. Sometimes, I could show you the plots of these orientations, but there's actually a subtler thing going on here. If you look at the cell bodies, often they're aligned in the same direction. You start to see it. Once you look at a row like this, you go, oh, and then you defocus your eyes a little bit, and you go, I wonder. Here's some more. You start to see it, but then if you make a quantitative image, you see that the cell bodies have the same symmetry as the fibers. It really shouldn't be too surprising. They're basically aligning themselves in the holes. You got fiber bundles going in these two directions, and the cells are, trying to take up as little space as possible, and so they're natural gaps in spaces that are also collinear. So it looks as though there's nothing in the available evidence that contradicts this picture. In order to support or deny, why were we able to see this on this day and it hadn't been seen before? The key to seeing it under a microscope was to use a plane of section that was coplanar with the turns. If you're not in the same two-dimensional plane as the turns, what you're going to see are little dots or little lines, but you're not going to catch both incoming and outgoing populations at the same time. There's a couple of other features of this that I want to call your attention to because they will disabuse certain other notions that are popular. One is that there doesn't seem to be any particular topographic organization to this. In other words, it's not like this is a highway with lanes where the bottom stuff in is the left stuff out, and then the next stuff is the next stuff, and the next stuff is the next stuff, where things are maintaining their relative positions as they make this turn. There's just not any evidence of that. Could be happening at some statistical level. Don't see it. That's certainly not obvious, point one. So this seems to, a lot of neurologists or neuroscientists think that this is the case, that topography is, for example, in a retinotopic map. This is actually quite well known for the optic nerve, that the fibers emerge from the eyeball in no particular topographic order. Then they establish a partial topographic order horizontally at the level of the chiasm, where fibers know which ones should cross and which ones not cross. And then they reestablish topographic orders at their targets, such as colliculus and visual cortex. But they're not terribly topographic while they're traveling. I've heard the same thing from Doug Rosine concerning motor pathways as they pass through the internal capsule and go into the pyramidal tract, that they're just not they're not topographically organized. They get organized at the other end. I think the same thing is true for the acoustic pathway and so on. Okay, there's a second point here that is even, I think, more radical, and that is everything's branching. We're not just seeing turns, we're seeing multiple branches. So the idea, one neuron, one target, well, whoever thought that really? We kind of already knew that that probably wasn't right. We certainly knew there were collaterals, but it seems as though we may have had to have our nose rubbed in the fact that collaterals are the story. I mean, think about it. Suppose the average neuron has 2 or more destinations. And by destinations, I want to say what I mean is we all knew, everybody knew that an axon goes to a location and then it terminally arborizes. So we're not talking about terminal arborization. We're talking about a single axon having multiple remote destinations. Now, we haven't proven that because we haven't tracked individual axons down to their destinations. However, there is a lot of evidence in the literature that that is indeed the case. Why would an axon be branching in the middle of nowhere unless it was sending 2 branches to remote destinations? It would be pretty weird and inefficient to have a branch here and then have both of these things then track for centimeters to a common target. So what does that mean? That means when people draw a diagram of connectivity and say, here's an area connecting to this area and area A connects to area B and area C, well, their network representation implies that the connections from A to B and from A to C are logically independent. they may occupy the same space, but they are different things. That should be called into question. They actually entail one another at the level of the single cell. Now, is that a difference that makes a difference? Time will tell. But the idea that collateralization, multiple parallel targets of single cells, is the norm, that the best statistics we can get right now indicate easily at least 5. Now, that opinion was, so it's funny, when you present these I mean, on the one hand, it seems terribly radical. On the other hand, the more you present it to people, the more they say, oh, yeah, this makes sense. It was a great moment when, at the Connectome project, a funny story. So we had an advisory board meeting with Carl Zelis on it. You guys know who Carl Zelis is. He's at Aachen, holds Brodmann's chair. And Bruce Rosen looked him in the eye and said, Carl, is he nuts? And Carl just said, "We knew this." So what would be the good news? What this means is that the project of inferring large-scale cerebral connectivity from fiber orientations as measured with diffusion MRI is incomplete. We don't yet have a complete working theory that covers all of the cases, to say the very least. Now, whether it covers some of the cases, most of the cases, or just a fraction of the cases is a still open question. Secondly, it puts a different spin on how the brain is built. What is this thing for? What I want to emphasize is that surveying anatomy, the degree to which this structure holds force varies. There are some places where you see tons of it, where it looks like this, everything is, 90% of the stuff is running in these two directions. There are other areas in which it'll be 10% of the stuff running in the two directions, and the other 90% will appear random. A good example for that might be the striatum. So the striatum is famously grid-shaped. It looks like a Japanese fan. Actually, I can show you pictures of that tomorrow. It appears as though the white matter of the forebrain is among the champions of the brain in terms of being densely filled with this grid structure in an extremely strong form. So why this structure should have taken such force in the deep cerebral white matter is an open question. There are a lot of possible theories. One, it might be, why not? Which is another way of saying things don't want to get lost. This is how evolution works. It takes something that was there and then it rewrites it and rewrites it. But I don't fully accept that explanation because in some places this structure is to a much greater degree set aside, like the reticular formation. There are areas of the diencephalon where you can't see this at all. So it appears that whether this structure is present or not is dialable, is controllable. And some areas have it, especially so. For example, the place where this is most dense of all is the centrum semiovalli. The corpus callosum and centrum semiovalli comprise a single cube, a very distorted one. Other places can't figure out what's going on. So, and by the way, here's another point. Note different axonal diameters. So this isn't just large axons. We actually checked this out, confirmed this with with immunohistochemistry with several axon specificities. So it doesn't appear that this is a fluke of the axons that we injected with this tracer. So, excuse me. What we'll discuss tomorrow, let's see, I don't know how we're doing for time. I'd like to talk. Well, the demo will be a lot of fun. I can describe what depends on which data you have online, but I think what would be, just to anticipate what we're going to do in the next hour, would be to try to identify a half a dozen or just one or two major white matter pathways, see what they look like. I was thinking, why don't you try to track down, and I'll give you a list, let's just try tracking down the cingulum bundle. Let's just get a hold of the cingulum bundle and see what it looks like. And then I'd like you to, for the advanced players, try to use a hidden feature in TrackViz, which is find the fibers that cross those fibers. There's a little button inside TrackViz that will show you all the stuff, the local environment of a bundle. So we can play that game with the cingulum bundle. I want, since this was an intro to diffusion, I had this whiteboard here to describe the physics of diffusion a little bit. And I wanted to give you two quick pictures. When we say, let's cut to the chase and talk about diffusion, and since Mark has already introduced this, I don't need to re-say the things that he said, but I want to equip you with some buzzwords so that when you hear other people talking about diffusion, you can maybe know a little more than the average bear about what they're saying. I want to describe two cases of diffusion that come up that are important in our thinking. Neither one of them is perfectly instantiated, and biology lives between these two extreme cases. So the first case is free diffusion. Does everybody know what free diffusion means? So the goal is not to be confused by it, but to try to simplify it. So imagine you focus your attention on a particle starting at a point. You're going to put, you're going to have a series of blue particles, red particles located at this point, and time is going to go down this way over time. So after one interval of time, let's just suppose that this particle is going to either take a step to the left or a step to the right, with probability a half, like that, okay? Everybody see what's going to happen? Okay, so you know what's going to happen. This thing is going to turn into a Gaussian, right? And you also know that it wouldn't really have mattered what model we used up here, as long as it wasn't creeping off in one direction. As long as it had a zero mean, it wouldn't have mattered whether we had shaped it like this or shaped it like this or given it any other shape, because by the central limit theorem, it would have always done this. So this is the free or unrestricted diffusion case. Okay? So when people talk about free diffusion, they're talking about this. Put in a speck of dye and watch the Gaussian get bigger and bigger and bigger. Now, as Mark pointed out, that free diffusion could possibly be anisotropic. I've done it right here. I've made this anisotropic without telling you, because this is one dimension, x. But as you know, the physical universe has a y and a z, and we didn't describe that. What I've implicitly done is made the diffusion go only in the x direction and not let it get off this. So this is actually inside a very thin pipe. It's like string theory. I've got this very thin pipe, and it's just turned into a Gaussian in this one axis. So free diffusion will look like this if it doesn't bump into stuff. What is it bumping into? By the way, why is it scattering? Do you have any idea why it's scattering? Why is it not just going inertially forever, bumping into other water? That's why they call it self-diffusion. That's the selfie part. What do you mean self? Self, it's bumping into other water. Hence, this Brownian ping-pong path. Where would that not occur? In outer space. If you have, the gas has to have a speed of sound. Things have to bump into each other. In outer space, the gaps are so large that a molecule will move ballistically forever. It'll just keep going. It won't scatter. So until you get to enormous scales. Unrestricted. Now let's talk about restriction for a second. Here's the one I really wanted to show you, and here's why I had this blackboard dragged out here, because it's so cool to see. Now this idea is due to David Corey, who wrote about this in the early 90s. Can't tell whether my glasses are over my ear. Okay, let's imagine a particle in a box. Is everybody taking quantum mechanics? No, not that box. A one-dimensional box is like this, and the particle is, I can make this bigger. I really want you to see this. Okay, here's the box, and the particle is here, okay? And the particle can move inside this space. Okay, let's call this space of length, let's call it length 1. Okay, now, and this space is full of particles. Now, of the particles in this space, how many are eligible to move 2 units to the left? Okay, let's plot delta x. So we're going to make a new plot over here. This is going to be number of particles, and we're going to call this axis delta x, which is how much did it move? We don't care where it started. We're just asking how far did it travel? Okay? So, delta x, so let's call this -1, +1, and here's +2. How many particles in this box are eligible to move 2 units to the right? What? Nope. Try again. What? What? Yeah, getting warm. None. None. There are no particles in this box that have the ability to go 2 steps in any direction, because the box is only 1 step big. How many particles in this box are eligible to stay put? All of them. So if you say how many particles could have a delta x equal to 0, well, let's just call this 1 in arbitrary units. So all of the particles are 100%. Call it 100%. That's better. So 100% of the particles, this axis, instead of number, we'll call this percent. Okay? That's a much better number. 100% of the particles are eligible to not move. Okay? Which of these particles are eligible to move 1/2 a step to the right? What? Yes, which half? Yes, exactly. These are you're playing the game. These are the particles that are eligible to move, that have the ability to move 1/2 a step to the left. The ones that start here are not eligible. They have no place, they can't go that far. Okay? So if this is 100%, then the ones that are at 1/2 a step to the left will be 50%. How many are eligible to move, I'm sorry, I've drawn it poorly, like that. How many are eligible to move 1 unit to the, I'm sorry, I'm dyslexic. I meant right. You said left. Okay. Ignore the words that I use. Watch my hands. How many particles are eligible to move 1 full step to the right? Yeah, almost none. Just the guys that are crowded against that barrier to begin with, 0. Okay, so only those guys were eligible to move that far. And you can see by symmetry what's going to happen in the other direction. Okay? Now, does anybody recognize, so we have this box, you can describe this original distribution here with a density rho of x, position as a function of x in this restricted environment. Can anybody see the definition of the relationship between of this to this? Anybody know a formula that links these 2 things? Let me make a picture of it, because rather than calling it by its fancy name, the picture will make it even clearer. What I've really done is to calculate the number that you just gave me. What I could also do is take this box and shift it a certain distance, like so. Okay, I've shifted the box, and then I've said, and what I've then done is measured the area in common to the original box and the shifted box. Now, does anybody know the mathematics that describes that? You take an object, you shift it over, you multiply the 2 functions together, and then you add, and you get a number. Convolution, exactly. So this is rho convolved with rho. That's what this shape is. Okay? So this was Corey and Garraway's result. In an infinite, so this is the time goes to infinity case. We just say, is it possible for the spin eventually to get there, ever? And in infinite time, in the restricted diffusion picture is the autocorrelation of the container. Rho is the container. This is the autocorrelation of the container. That's the result you needed. So if you have any container inside of the cells, of the tubes, of the what have you, of the muscle, the non-water space is the container. And the diffusion pattern is the autocorrelation of the container. And now you understand everything there is to know about diffusion imaging as we now practice it. So DSI, for example, is let's make a three-dimensional image of the diffusion pattern, which is that thing. Now, here's the thing. You know that an autocorrelation is a very lossy process. So you take the autocorrelation of an image and you have much less information than you had to begin with. And you know, and those of you who know the mathematics know the mathematical reason why that's the case. So this is an information lossy process. By the way, so if you had, for example, suppose the container was a circle, what would you do? You'd say, how many points are eligible to move over? You would shift the circle, and that overlap area would tell you how many spins were eligible, could have moved this distance. Or if it was some funny shape, you just copy the funny shape out and move it over, and that eligibility gives you the case. So in reality, diffusion is in between those two cases. You have some spins. When you start your diffusion clock going, you encode diffusion as Mark described, they start moving, they don't bump into anything, and they start to fan out. And if you waited forever, you would eventually get the autocorrelation of the container. Instead, what you're really getting is this mixed autocorrelation of the container, but it hasn't felt the whole container yet, because it hasn't had enough time. And on top of that, you don't have one container. You have all the containers in a voxel, this huge macroscopic thing, 1 millimeter across, and you're measuring containers on the scale of 20 microns. And so you're taking the average of the shape of the container, average over all the containers that you find inside a voxel. And now you know why we don't have as much information as we'd like. Well, okay, so that's all I wanted to say for now. And I hope we have a little time to look at TrackViz. Shall we just go directly into it? Do you want to take a break, or do you want to go, or do you want some questions? Yeah, sure.
So very interesting. I really like your philosophical orientation towards this. You mentioned one thing in the beginning, though.
That's because we're stuck. That's because they're forced into it because we didn't have the tools to build a healthy science. Go on.
You mentioned early in the beginning that if we inject a tracer in region A and then it shows up in region B, it's this connection we infer is a fact. And so I wanted to sort of think of a possible counterexample is if, given what you said in the beginning, we don't exactly know what we're looking at or what we're measuring, it's plausible that the connection is a functionally guided one, determined potentially in part by the state of the system as we were observing it. So,
oh, quite right. That's perfectly possible. So you have different tracer molecules have different characteristics. So it depends on the uptake of the molecule by the cell, and then by the, in the case of BDA, transport. So the uptake and transport properties are indeed functional properties, and they can be influenced. I mean, it would be completely different if the tissue was dead, for example. If the tissue was dead, you wouldn't see any long-range transport. And that, in effect, is a dye experiment. I mean, that's an extracellular tracer that is just doing just what the water does, except more slowly because iodine has a higher molecular weight, but it's just moving out. So you're quite right. So if you could repeat the experiment, so wouldn't it be wonderful if you could repeat that experiment under different tonic conditions? I mean, let me give you some fantastic experiments. How about just using different colors nearby each other? Okay, just make a map, a spatial map. But you're asking a really great one, which is, suppose you put in a color and then change the condition and then put in a new color. And you know what? You would have different uptake. So this is a problem. So you would have to be very careful about which dyes those are, because their molecular properties will determine, their degree of uptake. And so I think another question is it democratic? You know, are you really seeing, this is another question, are you seeing all the neurons, or are you only seeing a subset that took up the tracer? And it was, if I were presenting that material, I would describe, I said we did immunohistochemistry. So the immunohistochemistry was to say, let's look at all the axons. So are these axons that have tracer uptake indeed representative of all the axons in this volume? Because after all, the MRI is going to see all the axons, not just the ones that are connected in a particular way or take up tracer. That's what you need, that syllogism of connectivity, orientation of the paths of the connection, orientation of all the tissue that MRI will detect. Yes, actually the best experiments for that, I think, I would track down, go through the literature of Alan Koretsky. So I think that the manganese experiments done with MRI in non-human species precisely do have a functional dependence. And so the functional variability of transport is an amazing biological variable. And if only we had a way, using deuterium or polarized oxygen or something to see it in humans, it would be huge.
Hi, I was just curious, you mentioned the occurrence of some neurons that are in white matter bundles, and I was wondering the metabolic needs of those neurons in the vascular supply, microvascular supply, as well as the metabolic needs of restoring membrane potentials at the nodes of Ranvier or in axons that might be less highly myelinated, could create a sort of blood flow that's detectable in MRI within the white matter. The question's not really about diffusion imaging per se, but about this sort of increasing number of papers that are reporting bold signal in white matter bundles that correlate with cognitive variables like reaction time and so forth.
It's a wonderful target. I don't know the details. I do know that the microangiography of white matter is not that difficult to study. You can make microvascular casts that very efficiently show the scale and diameter and distribution of the microvessels. So it's nothing like random. I watch that literature with great hope that it will become possible. I'm especially intrigued by the experiments in which they cause a deliberate conflict between two regions, and then the white matter in between the two regions may light up. But that could be the way to crack this case. Moreover, as you know, there are also other effects. I mean, diffusion isn't the only thing that's orientation sensitive. I mean, T2 star is orientation sensitive. So there are, it would give us another bite at the apple if we could get that technology into a stable condition.
Mm-hmm. Thank you.
I was just wondering, this is not my realm at all, but I just find this really fascinating. And it makes me think a little bit of the canonical microcircuit model and how things are kind of set up in this really nice orthogonal way in the canonical microcircuit model. And I was wondering if you think that somehow this orthogonal pattern is kind of a stabilizing factor, and if that has something to do with why we have decussation in the brain.
Yes. No, I mean, there are a lot of that question of the structure-function relationship is infuriatingly intriguing, because unfortunately, you can make too many hypotheses. It's not that there aren't a hypothesis; it's that there's too many, and and perhaps we should talk about that tomorrow. What hypotheses there might be, and for example, in the cerebellum, it might just be packaging. On the other hand, this whole thing had to evolve from these simpler conditions, and so. Locomotion is the one common element. I mentioned to Mark over lunch, interesting article by Rafa Justa about what is the prototypic circuit of the cortex, in which he analogized it. He said maybe it's analogous to a coupled oscillator circuit in the spinal cord, which neither one of them I would say has orthogonal structure, but they do very simple geometries. Concerning orthogonal structure per se, The only things that I really know have orthogonal structure, let me think for a second, topographic maps. So certainly there are a lot of topographic maps in the world that are naturally orthogonal, such as acoustic, obviously visual, tactile, acoustic. And so if you look at the colliculus, for example, it's a cube. It's got two-dimensional maps stacked up. I can show you those images tomorrow. But that's not as strong a request as you're making. You're making an even more ambitious request, which is to say, does any non-trivial dynamics ensue from an orthogonal structure? And we can imagine mechanisms by which that might occur, but we have not identified a case where somebody says, we've seen something like this. It feels like, we're being taunted. I mean, there are so many things that are close in no cigar. You know that the grid cells of the entorhinal cortex. You know that there is a structural grid in the entorhinal cortex of recurrent paths from the hippocampus, which also, the calbindin positive cells occur in clusters in the entorhinal cortex. Those clusters form a hexagonal grid. People swear it's hexagonal and not a 6120-degree parallelogram. It's certainly not orthogonal. So the answer is we're looking. We're not even looking. We're thinking. The question is it more likely that we're going to find the case or invent the case? And I don't know. Okay. So let's move then to the program. There were one or two things that I was hoping you might do in order to get your feet wet. And one feature of this program is that the tracking algorithm stops when the fibers rotate by more than a certain amount per pixel. Now, if you think about that as a condition, can you see why we would want that to happen? Can you see why it's logical to do that? That's not a hack, that's just an expression of the nature of the reality of the data. See, suppose the fiber were to turn by more than 1 radian within a voxel. Could you still trust the orientation to mean anything? Yeah. You see, the orientation would become meaningless if the fiber is sweeping around by some larger than some amount, so upwards of 1 radian. But if it turned by more than a radian within a single voxel, you wouldn't really know anything about which way it was pointing. So, following the dictum of Wittgenstein, whereof one cannot speak, thereof one should remain silent. So if you don't know the connection, you got two choices. Keep going, you got a couple. Guess, keep going, or do nothing. We chose the do nothing because we felt that the false positive paths are more damaging to the overall value or integrity of the data. Others have made other choices. So Patrick Hagman, in trying to establish connectivity, kept going. The people who advocate probabilistic tractography do something in between. They're always sort of randomizing choices across possibilities. So this actually gives you a way to tell. So I want to say, what are some interesting examples? One interesting example is, can you turn the dials on the program to show the cortex? Do you have some data in front of you in which you could just show the intracortical stuff? And how would you go about that? You will find it very interesting to look at fibers of different lengths. Okay, let's say that. So looking at fibers of different lengths is one thing you ought to check out. Another thing you ought to check out is we have a dial for curvature. Now, what might that mean? Basically, it's a good way of picking out U fibers. And a third thing I'd like you to do is pick a pathway that you can name ahead of time and see if you can find it. But no, let me not say that. That's too hard. Go after the cingulum bundle. The cingulum bundle is a beautiful structure that is, you'll know exactly where it is. And why don't you see how widely connected you think it is? And also, what the effect is on how you pick it. Do you pick it with a sphere or a plane, or what is your method for isolating the cingulum bundle? Can you isolate it, more or less? And so you kind of have your own metric. You want to get as much of it as possible, and you don't want to get a lot of other stuff. You kind of want sensitivity and specificity relative to your own beliefs about what the singular bundle is like. So I think that would be, okay, so here's what I'd like you to do. 1, try to find the singular bundle. 2, try to find all the stuff that crosses the singular bundle. So there's a button in there, and I'll show you where it's located for the fibers that come from a fiber. It's a little hard to find. So why don't you try that, and I trust you all have a toy data set with a track file in it. Oops, never mind. Okay, so maybe we're not doing a demo. In previous years, that had
Advanced talks inevitably engender as many questions as answers. But the good news is that he's going to be staying with us. We'll be hearing from him tomorrow. Lots of chance for discussion about the stuff that becomes more controversial, and that'll be great. And so Jesse's next. And do they have 5 minutes to pee while you set up your slides? Or? Okay.
Okay, so we've shuffled things around in the schedule a few times, probably since you've been here, but also before you got here. I was originally slated to follow up Agatha's talk on functional connectivity methods this morning, and she went into psychophysiological interactions and partial least squares analysis. And I was just going to chime in with sort of a brief presentation about another method that I co-developed a while back called beta series correlation method that is still being used, and it's recently gotten sort of updated by some other labs. And so I have about a 30-minute or so presentation on that I could give. That's what I'm scheduled to give. Or I have another presentation I've given past years about artifact detection for fMRI. That's a little bit more sort of practical discussion of how to look at motion-related artifacts, global signal artifacts, and scrub them from your data. So I was just wondering sort of what people would be more interested in hearing. There's a chance I could squeeze whichever one I don't present today in the schedule tomorrow if there's any slack, but I haven't looked that over yet. So how many want beta series correlations, a functional connectivity method, sort of a alternative to PPI? Yeah, raise your hand. Okay, it's maybe about half of you. I won't count at this stage unless we need an official count. And how many want the artifact detection and removal? It seems like it's people want both presentations. Okay, well, maybe I'll do the beta series today because that's on the schedule. I'll try to keep it brief so that we can transition to more of the student introductions and two truths and a lie. And then we'll see if we can squeeze another 30 minutes in tomorrow for me to do the artifact detection. I'm not going to be here next week, otherwise we could bump it down. Okay, yes, and the break, yeah. So if you want a brief break, use the restroom, check your Twitter feed. Yeah. Oh yeah. Good. It's good time for you to do that. Yeah. Yeah. Okay. So take a break. I mean, I have I don't know what. Okay. She wrote to you? Yes, thanks, exclamation. Okay, so you want to plug in here?
Yeah, so I'll just be quick. As soon as everybody comes back. Yeah, don't be shy. Okay. People are still outside. Okay. All right, so I think everybody's here except for one person, so hopefully the person will come in before. Okay, debates. So the last day we're doing debates, and you're going to start getting into your teams today. So I want to talk a little bit about the debate format, and did that, geez, that's so funny, it's not changed on my screen, but it is on yours. That's so weird. Okay. So first, debate questions. So we've narrowed it down to 7 questions, and what we're going to do is have everybody just take a second to read all of these, decide which 2 you like the best. We're going to choose the top 3 voting, the top 3 votes. Somebody's going to have to write down the numbers for me because I can't remember them. So everybody take a second to look at them. I would read them off, but I can't. Okay, all right, so resting state versus activation imaging, what's better? Should functional imaging be used in the law or in courts? Lie detection, basically. Is fMRI relevant to cognitive psychology? Big data in fMRI, fad or future? Utility of fMRI for understanding brain function, is there room for more discovery? Is functional connectivity by fMRI biologically meaningful? Can machine learning allow us to understand brain mechanisms? Before you vote, I should tell you a little bit about the format, then because that might change how you decide to vote, okay? So these are not meant to be serious debates. They're meant to have serious content, but not necessarily presented in a serious way. So the format will be this. There will be 3 groups, and each group will have 2 teams. You'll be randomly assigned with a coin toss to your debate topic, and then randomly assigned pro or con. You can do any format you like. You could sing. You could do a skit. Most people just would do a skit, but you could do songs, make up your own songs. You could do a rap, or you could just be serious. Each team will have 10 minutes to present their argument, and then after each team presents their argument, there'll be 3 minutes for the other team to present a counter argument to their argument. So it'll be team 1, 10 minutes, team 2, 10 minutes, and then team 1 can present 3 minutes. So that's going to be some real quick thinking over there. We'll probably have a few minutes break there. And then the reverse. And then everybody can do some Q&As and a little time for some improv, and then we'll vote. And the judging is, there'll be 2 things will be judged on. One is the most convincing argument, and the second is the most creative or amusing presentation for each group, and then overall there'll be a best team showing a combination of creativity and convincingness. Are there any questions? Okay. All right, so with that, we're going to vote on the topics now. So how many people would like resting state versus activation image? You get to vote for 2, but don't vote for more than 2, okay? So resting state versus activation imaging, what's better? How many like that? Okay, Martin, you don't count. Okay, all the way up so I can count you. 1, 2, 1, 2, okay, decide which way you're going to go. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12. Did everybody get that? Okay, somebody writing that down? Okay.
Everyone gets 2 votes.
Yeah, everybody gets 2 votes. Okay. Should functional imaging be used in the law? How many people like that? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Is fMRI relevant to cognitive psychology? Okay, we got 1. Strike that. Big data in fMRI, fad or future? Big data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Utility of fMRI for understanding brain function. Is there room for more discovery? 1, 2, okay. 4, okay. Is functional connectivity by fMRI biologically meaningful? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 12 because somebody voted twice. Okay, 12. Okay. Can machine learning allow us to understand brain mechanisms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 I got. Okay, so Mark, what's the final tally? What are our 3 questions? But we got 3, so one's. Shit. Okay. Oh, sorry. Okay. So which 2 are a runoff?
Number 1, which is resting state, and number 6, which is functional connectivity.
So those are the 2 that are like we have to dump one of these, right? Okay. Okay. So now you get to vote for 1. Resting state versus activation imaging. Okay. No. That was not that. Thank you. Okay. Big data. Should functional imaging be used in the law? So now you're voting for resting state and functional connectivity. Resting state versus activation imaging, what's better? And is functional connectivity biologically meaningful? So how many vote for the resting state? I'm sorry, resting state versus activation imaging. Okay, up or down? Skits. 1, 2, 3, 4, 5, 6. Martin, you can't vote. 7, 8, 9, 10, 11, 12, 13. And how many vote for is functional connectivity by fMRI biologically meaningful? Okay. All right, there you go. That has it. That's more than. Okay. So the 3 that we're left up with is functional connectivity biologically meaningful. Should functional MRI be used in the law? And big data, fat or future? Okay, is everybody happy with those? Is there anybody want to lodge a complaint?
Should we could reduce the team size and do 3 debates, no?
We already have 3 debates. We can reduce the team size and do 4 debates.
Oh, yeah.
We could do that if people wanted to, but right now we've got like 6 people per team, so it might be hard to reduce it anymore. Okay, all right. So, Mark, you got the circles because I won't remember.
So I have big data, law, and functional connectivity.
Okay, is everybody happy with those 3? Except for Martin? I thought for sure that one would win.
I don't want to debate our topic selection procedure.
Okay, so so I told you that. Okay, so here are your teams, okay? So this is debate group 1, team pink. Everybody see your name? Amanda, Christian, Eva, Sichun, Adam, Julia, and Cyril. Take pictures if you forget. Okay. Team red, Julia, Philip, Mariel, Maggie, Taylor, and Matthew. We tried to have a mixture. I tried to mix up different seniority and all. Well, I did the best I could. What can I say? Semi-ran it. Okay, debate green 2. Team yellow. Sorel, Hengi, John, Micah, Erica, Dina. Team green. Wu Yang, Danielle, Chun Liang, Masa, Donna, Willem. Everybody got it? We will, but, you know, just so you all know. Okay, Jorge, Kiara, Taihao, Amy, Elizabeth, Zhao in the team blue. And finally, team purple, Keen, Yunji, Edward, Denise, Natalie, Tasha, and Catherine. Oh, I'm sorry. No, is that right? So it's supposed to be above. So who is, did I screw up? So who's Papa? 1, 2, 3. Okay, gotcha. Got it. I just want to make sure I had the right number of people. Okay, all right. Okay, everybody got it? Okay, all right. That's it. Back to Jesse. Okay. Here we go.
Lots of voting this afternoon. Okay, everyone's still cool with this choice of topic? Should we vote again? Let's see. Why is it? It's a third-party brand connector instead of an official Apple adapter. There we go. So I have the pleasure, once again, of getting you at this amazing time of day when your minds are finally peaking in their attentiveness. This is a connectivity method that I developed along with a collaborator, Adam Ghazali, in Mark Desposito's lab when I was studying graduate school. And we were interested at the time in modeling interactions between brain regions during tasks that had a set structure of events that occurred within a trial in a particular sequence that we could not randomize, and that the events were sort of closely spaced, and the way that they were spaced was constrained by the psychology of the task. And the task that I was working with for the most part, although this is certainly not the only kind of, I'm trying to resolve this static in the signal here. Maybe it's this microphone that's the problem. So the sort of paradigmatic task that we developed this method for is a task like this. It's a delayed response task. Many working memory tasks are like this, but there are also other kinds of attention tasks, anticipatory processing, reward processing, that have multiple event subtypes that happen within each trial. So in a delayed response working memory task, in the simplest scenario, you would have a picture that's presented or some form of stimulus that the person needs to encode. We'll call that the cue here. And then a period of time, several seconds, I mean usually about 8 to 10 seconds in these kinds of tasks, a maintenance period, we'll call that delay here, and then a probe stimulus, and the subject in this particular paradigm would decide if it matches the cue. And in the past, researchers had done functional connectivity studies in working memory tasks, but usually block design type tasks like the NBAC, where you do 20 to 40 seconds of memory sort of encoding and maintenance at one load, and then you switch the load, and you can do connectivity easily using time series correlations or psychophysiological interactions with block designs. But for an event-related design, it's a little more challenging, because we wanted to not just see how brain regions are interacting across sort of the entire trial, but really in these individual component stages of the trial. And many tests are like this. There's different cognitive processes engaged when you first encounter the stimulus than when you have to sort of maintain it. In the absence of any environmental stimulation, now you have 8 seconds that you're supposed to hold on to this face, and the better that you're able to do that, the more accurate it will be when you get the probe and make a response. So we wanted particularly to look at functional interactions between brain regions separately during these different task stages, in this case cue, delay, and probe, but it could be anything. So in a hypothetical task responsive voxel, in this kind of task, let's say a voxel in prefrontal cortex, you get a time course for each trial, and if the delay is long enough, it usually has these sort of 2 humps that brain regions respond strongly when a stimulus is present. They drop off when it's absent, but not always down to baseline if there's some maintenance activity. And then it comes back up. And you get different responses for different trial types, and these are just drawings of like hypothetical data. Real data aren't quite this clean. And in a typical univariate analysis, if one was to model this the way that it had been done for a while up to this point, was just to have one regressor that's sort of a HRF-convolved regressor that's going to model the encoding period, the cue period of every single trial in your experiment. So if your experiment has 30 trials, it would sort of be this one shape that every time the encoding happens, you're saying, well, I hypothesize that brain activity will go up, sort of maintain for the duration of the HRF response, convolve with the duration of the stimulus that you're presenting, and then go back down. And you try to get a fit of that regressor to your data that can best accommodate all of the trials in your experiment. So you get one answer. Sort of here's my beta map or parameter estimate for the Q period, and then you get a map for delay period, you get a map for pro period. You put these different regressors. Now, what we did with the beta series approach was first to just run a different kind of GLM, and this is much more commonplace nowadays. It's used for analyses well beyond functional connectivity. It's a GLM with a lot of free parameters. Instead of having one regressor per trial type, you have one regressor per trial per instance. I mean, really one regressor per event within each trial. So one for the Q period of trial 1, delay period of trial 1, pro period of trial 1, and so forth. And these all start out with just sort of an HRF shape convolved with some boxcar, short boxcar, and then they scale to fit the observed data. And so each one of these regressors, when it fits the data represented here in the red line, will provide a beta value. And you could get these beta values for every trial. Let's say we had 50 trials. Well, every trial in this voxel will have a slightly different activity. And usually we're just interested in the mean. So this time series, or what we call a beta series, in blue would represent the single trial activity estimates during the delay period, because here I'm just showing you the delay period ones, in one voxel in the brain. Let's say the blue one is a voxel in prefrontal cortex. And so it has a mean activity, which is usually what we look at, but it also fluctuates. And the fluctuations are largely going to be noise, because the fMRI data have noise in them. The subject might be moving, their attentiveness might differ, their sort of breathing rate, and all kinds of things could be contributing to this variability. But the hope is that it's not all noise, that these fluctuations are also related to the degree to which this region is engaged on that particular trial, which is a little different from this trial and this trial and this trial. And the hope is that other voxels in the brain would have similar trial-by-trial fluctuations in their activity during the delay period. And if they did, the inference we would like to make is that these two regions are communicating with each other. I mean, it's just correlation. We're not showing that one region is transmitting information in a sort of a causal way to the other region, but that areas that fluctuate in synchrony across the experiment, shows correlated trial-by-trial fluctuations, might be interacting in some way. So this red voxel has a reasonably strong correlation in this example, 0.7 with the blue voxel. And so they would have functional connectivity at that level, R equals 0.7 during the delay period. And you could do this for a seed region to every voxel in the brain and create a connectivity map, and I'll show you examples of that. You can also do it for a set of ROIs. You could have 2 ROIs. If you're interested, maybe you're just interested in sort of left motor cortex and right motor cortex, or you could have a whole network of ROIs. So this can be done just by running a different GLM where you have many more columns in your design matrix. Instead of one regressor for each trial type, one regressor for every trial, or even in this case, 3 regressors for every trial. And that's how it works. This is just another illustration of the difference between the standard GLM and what we sort of casually refer to as the trial-wise GLM, or single trial GLM. People more recently, in the last few years, have tried to give this a more formal name, and I'll come to that at the end. But the standard GLM, you have sort of, these are the same color, blue, sort of indicating that this is just one regressor. It's up here, it goes down to 0 for a while, then the next trial starts, it goes up again, and so forth. So you get one answer for it. The blue regressor tries to best accommodate all of your trials. Variance across trials is bad for the fit, and similarity across trials is good. The trial-wise GLM uses free parameters for every trial, so you're probably overfitting the data quite a bit because you're giving yourself a lot of flexibility to model chance fluctuations that are just happening. But you're, again, hoping that there's some meaningful neural activity that's being translated to these trial-by-trial fluctuations in bold that might reflect regional interactions. So we first wanted to test this approach just with a case where we thought we had some sort of gold standard to look at. And it's hard, like with the working memory task, we have theories that maybe prefrontal cortex interacts with visual areas, and that's important for maintenance, but we wanted something where the theories were less speculative. So we just use a simple motor coordination task. When you're doing bimanual motor coordination, meaning your 2 hands need to interact with some precise timing, that presumably would require more connectivity between the right motor cortex and the left motor cortex. If the hands need to do things with kind of interleaved timing, that's going to place demands on interhemispheric connectivity. So we had two different tests. The control condition was this, what we called right then left. So subjects tapped a sequence with their right hand and then tapped a sequence with their left hand. And it took about 2 seconds to tap the sequence. It was just 4 keys with the right hand and 4 keys on the left hand. And they learned these sequences. And when they got cued right then left, they did right hand then left hand. The interleave condition, they had to go sort of right, left, right, left, right, left, right, left. So they played 8 keystrokes. It took about the same amount of time, except they had to coordinate the timing. So once one hand went, then the other hand went. So the motor cortices have to communicate more, presumably. So the hypothesis here is that the interleave condition should show more interhemispheric crosstalk. And so the interesting thing about this sort of experiment, we used a data set that had been acquired by a colleague of mine in the lab. And when you look at the univariate activity across these two different conditions, it's really identical. So just looking at it side by side here, whether you're doing bimanual coordination or right hand then left hand, you get motor cortex activity. The bold signal sort of on average is pretty high in both right and left motor cortex, and you can't really distinguish them. But when you place a seed in a region, I'll show you a seed in left M1 that we define I think anatomically for each subject. And then we look at its connectivity with every voxel in the brain. You can see in the bimanual coordination condition, the beta series correlation with other voxels in the brain is particularly strong in the right motor cortex. We also see some sort of somatosensory regions as well, regions that had univariate activity. But you see this other hemisphere prominently. You don't see it in the left. I guess I don't have the direct contrast here, but it was sort of confirmation that the interhemispheric connectivity was being reflected in correlated fluctuations in the beta series. Here's just another way of depicting this. This correlation is not a voodoo correlation because these two regions were defined by independent anatomical ROIs, so the left M1 and right M1. So when you look at their connectivity sort of as two ROIs in the two conditions, you could just see each one of these dots is one trial. And it's just the beta estimate or the activation parameter that came out of your GLM for that trial. And you're looking at left M1 as a function of right M1. And you can just see they're more related to each other, more correlated in this interleave condition than in the right then left condition. So that was sort of initial validation. And then I'll just show you sort of a couple things that we did with it. I'll try not to focus as much on the cognitive neuroscience and a little more on the method, but this, I think, gives some intuition about how the method is applied. So we were interested in the idea that frontoparietal areas would interact with task-relevant sensory areas to maintain that information working memory. So if you had a face that you had to maintain, face is going to be strongly processed in areas like fusiform cortex, but then areas like the prefrontal cortex would interact with the fusiform cortex to hold that information online. And in this initial validation we took, or not a validation, analysis, we took data from 17 subjects. They maintained the single face across a 7 to 8 second period. We defined a seed based on an independent localizer. So this is one decision you face with any connectivity method, including what you heard about this morning, PPI or seed PLS. You have to have a target seed. It could be based on an MNI coordinate with a sphere around it, or it could be based on individually localized regions in the subject's own brain. In this case, it was different for each subject, but based on a separate localizer task to find the FFA. And we just want to see which regions in the brain show correlated fluctuations with the seed during each of the task stages, the Q period, delay period, and probe period. So this is just the side note about defining the seed. Yeah, as I talked about yesterday, when you define ROIs, there are different approaches. You could pick a region that showed an effect at the group and then reverse normalize it to each individual subject. We can use a whole anatomical region. You want the whole putamen, for example, or allow it to vary for each subject, but within a constraint. And these will really affect your results. So for any functional connectivity analysis, you sort of have to decide, if you're using a seed region, is it a well-defined seed region? Okay, so just to sort of illustrate, if you look at the univariate activation, just the fit of the regressor that tries to model all trials of a given task stage, you see there's more activity in the brain, many regions when they see the face cue and when they see the probe, and there's not much happening during the delay, but a few areas show above baseline activity. just sort of contrast the beta versus 0. A lot of areas do go pretty low, actually drop negative. But with the functional connectivity, when we use the right FFA as a seed and then do a t-test on the 17 subject group maps, you can see that areas here, like the right inferior frontal gyrus, show significant functional interactions with the right FFA seed during the delay period, despite having pretty low activity. So many areas seem to have coupling with the FFA during this period, even though the overall bold signal is dropping. And this is just an illustration more than a data figure of what that would be. So you could have two regions that have high activity, as they do here during the Q stage, and have lower connectivity. So in these two voxels, or two regions of interest, they have a R of like 0.35. But you can have a higher correlation, like a 0.6 correlation with lower activity. So the mean activity of a region doesn't necessarily mean that it's going to have high or low functional connectivity with other regions. Regions that show some degree of task responsivity definitely have the potential to show the most functional connectivity. It's usually the case that regions that are highly task responsive might be ones that are interacting with other task responsive regions. But some regions just have lower activity, and still the trial by trial fluctuations during that low activity period could correlate with trial by trial fluctuations in other regions. So that's the basic idea here. This is just a group map, a broader map of that. Okay. And when you use a white matter seed, just as a control, you don't get broad connectivity with cortical regions. So these kind of demonstrations, I mean, were useful when we were first developing the method, but it's a property that you'd want any connectivity method to have, that if you were just sort of picking up on some noise characteristics of the data, you wouldn't want to see it in white matter to show broad connectivity with cortex. Although I did just ask Van Wadine that question about white matter bold activity, and there's this resurgence of interest, like a half dozen papers or so in just the recent years about white matter bold signals. So maybe the fact that the left white matter seed correlates with the right white matter seed does mean that there's something consistent about bulb fluctuations within white matter, but it could also just be similar noise characteristics. Okay, that's just an aside. So because I want to get back to sort of methodological factors for those of you who might want to implement this kind of an analysis on your data, you'll sometimes see, if you look at the individual subject connectivity maps, that there are subjects who, with a given seed, will show really high connectivity with many brain areas. So you'll look at the map at a specific threshold. It could be an R value if you're looking at the raw R map, or maybe you transformed it to a Z-score. But whatever you specify, whatever threshold you specify, at that threshold, this subject might have broad connectivity with many cortical regions, and another subject at the same threshold could have almost nothing that survives. And so there's really differences in the sensitivity of subjects. And this isn't just sort of a beta series phenomenon. You'll notice this in other kinds of time series connectivity, resting state, and things. And so I just brought this up to pose the question of sort of what's the meaning? Why does this subject have a mean? If you look, this is a histogram of the entire brain. If you just look at every voxel in the brain and what's its connectivity with the seed transformed to a Z-score. And it's just very right shifted. Like, it could be that many areas of the brain are actually interacting with the seed, or it could just be that there's sort of this global signal that's riding on top of the meaningful task-related signals. And so wherever I put a seed in the brain, I'm going to see lots of connectivity, because regions' fluctuation over time is governed by other things. The subject's head might have moved, their sort of physiological state, their heart rate or breathing rate might have changed, or level of sort of hypercapnia from breath holding. I mean, all these things could create dramatic global changes in the bold signal, which is the subject really for the artifact detection talk. But it's just something to think about. So here are some potential solutions. So you can regress out global signal, and this is something that's done a lot with resting state analysis. So there's some controversy about it, because you're artificially shifting. When you remove the signal of the entire brain from every individual voxel, you're going to ensure that about half of the brain shows positive connectivity with your seed, and about half the brain shows negative connectivity with your seed. And that could sometimes give you the impression of anti-correlated regions or competitive interactions, when really you're sort of shifting. You're taking something that would have been a low correlation and making it a negative correlation
and something that would be a high correlation may get a little less high. But this is something that could be done, or you could pick regions of no interest like ventricles or white matter outside the brain and just try to regress that out to clean up your data, and regressing out motion, other things, all the things that are good for cleaning up your data for non-connectivity analyses could also help sort of deal with some of the imbalance between subjects. You can also get around this to a large extent by contrasting maps with the control conditions. So if you just want to see sort of what's the functional connectivity with my seed during this one task, you might have problems because the global connectivity is dominating. But if you have two different task conditions, well, now the sort of subjects who have this global increase in connectivity should have that for every task condition if it's just something related to sort of physiological or scanner artifacts. And so when you do the contrast, hopefully that would get washed out. It would be subtracted out. So if you look at the change in connectivity from like an easy condition to a hard condition on the task, that could be a meaningful metric. You can also ensure that outliers are not present in the beta series seed. So when we talk about the seed region, we extract its beta series. If you have 50 trials, you'd have 50 different values there. And maybe one of those is an outlier. And if that's an outlier, it's going to propagate to every other voxel because the seed is the region you're correlating with every other voxel. But you could also check each voxel you correlate to see if there's outliers there. You could just sort of build into the code a search that if there's a voxel who has a beta value that's like 4 standard deviations above or below the mean of its other beta values, to throw that out and recompute the correlation. And I think that's perfectly reasonable, if not advisable, to do. I might skip this because it's a little more related to the cognition and less the method. I'll leave you this slide. This one, I mean, these are just some other papers that have done this, but in the interest of time. This one is interesting because they tried to do something a little bit different in a lot of the work that I've done and other people who have used this method have done. You have this sort of multi-stage trial, or you can even use it for task design, so you have a single event on each trial. And then you get your connectivity maps and you contrast them across conditions. But this study looked at how similar is the connectivity of the brain during one task stage, like encoding a stimulus into working memory, as it is to the next stage, the delay period. So one of the advantages of the beta series method is this ability to get connectivity maps for each sort of cognitive stage of a trial. And in this case, you just look at how similar the connectivity is from one stage to the next. If the connectivity pattern is similar, that could be advantageous. That means they're maintaining sort of the connectivity state that they set up during encoding and sort of maintaining it into the delay period. And in this case, subjects who had the highest performance on the task showed the most similar connectivity from the encoding to delay. So I don't know exactly what this metric is, but yeah, the connectivity similarity from encoding to delay was associated with improved performance. So it's just a nice sort of extension of this method. Each dot here, I think, is just one subject. Okay, so pros and cons of this method. It can examine functional interactions between regions as they sort of evolve in a multi-stage trial. It's relatively simple to implement. Oh, I don't have a demo to follow, but you could look at previous years and download the demo and try it out. And there's also, maybe I'll try to post a link. There's someone, a previous NITP student, implemented a version of this method and sort of shared the code and a little video on his website. And I think that's quite good as well. I've not sort of supported this as a software release package. If I did, it probably would have even gotten more prevalent. But yeah, I don't have, other than the code that you'll find in last year's NITP demo. Yeah, I don't have a demo this time. The cons, it cannot directly determine, this applies to other connectivity methods as well, but it cannot directly determine whether these interregional interactions are direct or indirect. So there could be a third region that's sort of driving activity. The thalamus could be sort of coupling with the prefrontal cortex and with the parietal cortex, but they're not actually talking to each other. So that's a broad concern about connectivity methods. As I've already said, single trial activity estimates are noisy. So you can get these single trial estimates. You can do things with them. You can correlate. You don't have to do connectivity. You can correlate them with performance metrics on the trial, sort of how well did they do on the task on that trial. And sometimes you'll find relationships, but this is as if like that one little segment of bold data was supposed to capture everything that was going on in that trial. And we know that we designed these hour-long fMRI studies to reduce the noise. So when you get to single trial level, even with a very compliant and still subject with low head motion, still the single trial activity estimates are noisy. So you'll see that in the data. And you need a lot of trials to do this method. You shouldn't do it if you have fewer than 20. But ideally, you'd want like 30 or 40 in each condition or more. And the serially positioned, like these time-shifted HRF-convolved regressors, are still like a mediocre or even poor approximation of the actual neural activity. We're just, in this case, with a working memory task, we model the cue. Let's say the stimulus is 1 second, you sort of model that as a 1 second event convolved with an HRF. But the delay period might be longer, like 8 seconds, and it often helps to just, instead of modeling the full 8 seconds, to just put another little short regressor in the middle of the delay period so that you're trying to capture the variance that's happening during that time. And so it's a poor approximation of the neural activity, which should be persistent firing of any area that's involved throughout the delay. And it's really just done out of convenience to try to get a good estimate of delay, having removed variance that's due to the preceding cue period and the ensuing probe period. And it's not, excuse me, it's not ideal for rapid. Can someone get me a glass of water thing? Not ideal for rapid jittered event-related designs. So this has become a major limitation of the method, because in order to have very efficient univariate designs with lots of different trial types, we often want them to be rapid and jittered. So events are occurring every few seconds. You don't have really long ITIs between trials. You don't have really long ISIs between stimuli. And even the jitter itself is disadvantageous. When you're trying to model single trial activity, it's useful if all the trials and the event types are always equally spaced from each other, because at least any contamination of bold signal from one, sort of lingering bold signal from one trial into the next will be constant. That on trial 13, it's got a little bit of sort of the residual signal from trial 12. But if trial 12 and 13 are really close to each other, and trial 13 and 14 are further away from each other, well, in the later case, you've sort of let the brain relax much more, and you're sampling activity at a very different state. And so to say that now the fact that this beta value on trial 14 is higher or lower than the one on trial 13, and then that's sort of a meaningful thing, well, it could actually just be due to the jitter, that you gave the brain more time, more spacing to recover from the very sluggish, bold response to the preceding stimulus. So in these kind of designs that people do beta series for, it's usually good to have a lot of spacing between trials, but that comes at a cost of time. But this new approach by Jeanette Mumford and Benjamin Turner and colleagues, including Russ Poldrack and Greg Ashby, so has really improved on the ability of the beta series correlation method to do this. And they developed this not necessarily to do functional connectivity analyses, but to use single trial activity parameter estimates to do multivoxel pattern classification. So tomorrow I'll talk about MVPA, and I'll mention this again, but the same approach is also useful for functional connectivity. And so they just did a little tweak to the way we run that trial-wise GLM that actually has some really useful attributes. So the approach, which was first presented as a SFN poster by Turner and then written up formally in that Mumford paper, is to estimate each trial's activity through a univariate GLM. And you include, use your regular GLM, like usually you would have a task and you'd build some sort of univariate GLM that has your different event types for your standard analysis. But in this case, you just take one trial and then you pull that trial out of the rest of the GLM regressors and give it its very own regressor. So it's kind of this hybrid between your standard univariate GLM and the beta series style trial-wise GLM. In the trial-wise GLM, every event gets its own regressor. In the standard one, every event of a given condition gets sort of a single regressor that accommodates the whole run. And in this case, you just pull one trial out. So it looks like, I think I have a visual illustration. So the way the beta series method works is like, if each one of these is the onset of a trial, or an event within a trial, it gets its own regressor. This is the beta series method, which they renamed the LSS approach, the least squares separate. So beta series is now called they renamed it LSA, least squares all. So you have one regressor. Each trial gets its own regressor. They call it LSA. Least squares separate approach means you run separate GLMs. So if you had 100 trials, you would run 100 GLMs. Each GLM has one or more regressors to accommodate all the other stuff that you care about, and then one regressor of interest. That's the, in this case, trial one. And all you're going to care about in this GLM, it's going to give you, in this example, it'll just give you 2 betas. It gives you 1 beta for trial 1 and 1 beta for the rest of your experiment. The way that they actually recommend doing this is you'd have you get 1 beta for trial 1 and 1 beta for all the other conditions in your experiment. So if your experiment had 4 conditions, you'd have 1, 2, 3, 4 more columns. So if your conditions were cats and dogs and horses and snakes, you would get 1 for each of those. Plus you'd get 1 for trial 1, which has been pulled out of the other ones. And now you do that again. You run the GLM again, and you leave out trial 2, and so forth. And all you save is the beta map, the whole brain beta map for the trial that you left out. And then you put those all back together, and now you have a beta series. But it turns out to be better than in most cases, better than the beta series you would get if you run this model. And you could use that you can use the single trial maps for multivoxel pattern analysis or representational similarity analysis, where you're trying to decode different cognitive states. Or you can use them to do functional connectivity using the same kind of approach I just described. Here's just another illustration from a more recent paper from Rick Henson and his colleague Abdul Rahman. So the LSA approach, which is the beta series approach, sort of 1 regressor for each trial here, so forth, ... And the LSS, you have 1 GLM for each trial. The LSS seems like it'd be a lot of work if you were doing this in the GUI and running 100 GLMs for each subject. That would be a lot of work, but it's implemented in the AFNI package now. They have a tool to do this. I believe Jeanette has she's at least shared code with me. I don't know if it's available online, but there is, Jeanette Mumford has created FSL implementation of this. It also can be implemented using scripts. If you know how to create scripts to build your univariate GLM, it's not that hard to code a lot of different GLMs that will just run in sequence and get saved in different folders. So this is the LSS approach. I've seen it used a lot since this paper came out, especially for MVPA. And the LSU is just the least squared univariate. This is the standard approach. If you had 1 condition of interest, you would just have 1 column in your design matrix, and you would get 1 beta. So that's all I wanted to say about this method for today. Do you have any questions? Okay.
So in the LSS approach, do you really remove the first trial at all? So it's just 1 for the first trial, and in the second beta, the whole thing that you have, you don't have the first trial, right?
Yeah, you pull that one out. So if your experiment was just like 4 different types of visual stimuli, like those animal examples, and the first trial happened to be a snake, and you would remove that one, it would just be called trial 1. You'd keep track of what it was somewhere in your, I don't know, a MATLAB or Excel spreadsheet, but that would just be trial 1. You'd get its beta. And then all the other regressors, you'd have your other regressor that models every cat, another one for every dog, another one for every snake, but the one you pulled out, and one for every horse. So, yeah.
I have some question about the schematic, the picture of the 3 overlapped. Can you go back to the slide? Maybe one of the very first slides.
Oh,
and you estimated a single value from a black line, which is the summation of 3 lines or 3 events right here.
So no, this black line here?
Yes.
Oh yeah, I wish that line wasn't there. It was just in this figure that I was pulling out of somewhere else. This black line is like the hypothesized aggregate signal, yeah. But no, I guess it is what you're saying. It is the voxels time series that you're then trying to get 3 numbers to estimate it. Yes, so that's right.
Oh, so do we estimate only one beta from each trial, or do we estimate 3 betas on each trial?
3 from each trial in this example, because these trials last about 10 seconds. And some experiments have done the trials last even longer. Like I did one experiment with, so it started with 6 seconds of auditory stimulation and 4 seconds of visual stimulation and 9 seconds of delay, and then like 2 different probes. So you could have more betas in each trial, but the more that you crowd those together, if their onsets are like less than 3 or 4 seconds apart, they'll start to become highly collinear. And because you don't have other events later in the experiment that you're trying to fit, that collinearity just ends up really messing up your estimates. Yeah.
Thank you.
And you can look at the collinearity of using the kind of tools Martin talked about.
Yeah, I'm just curious whether, if we do the standard, approaches, then look at the deviation at each trial, whether the deviation correlated, so that in effect would have similar thing.
So the variance across trials correlates with the...
Right, so so instead of evaluate beta for each trial, if we just have a single beta, and then at each trial we look at, how much deviated from your prediction. So then whether these deviation correlate.
Oh, yeah, that's interesting. You'd have to figure out how to measure that deviation, because when you run a GLM, you just get one error term for the whole GLM. So every voxel is fit by all of your regressors of interest, plus the regressors of no interest, which might be like motion parameters and linear drift effects and other things that you put in there. And then you just get one residual mean squared error. So for the voxel, it tells you how badly your entire model, with all that you put in to try to, you put in your best model, but there's still something that's not explained. And so in most GLMs, you just get that one number. If you wanted to go look at the deviation on each trial, you would have to go back to within each voxel, you'd have to go to its time series and see how well some combination of the regressors was able to reconstruct the signal during that window of time. It is an interesting idea. I bet there is some way that you can sort of measure that deviation, and perhaps that would be a measure that would be useful for looking at single trial activity. Yeah, but just a different flavor of the same approach.
Hi. For instance, hello. Yeah. I'm wondering. So for instance, in one trial, there I have 3 conditions of interest. So in this case, what you have shown here is that we have 3 beta, right? For each 3 beta and each beta for each condition of interest. And if I use the revised GLM model, then in this way I should do not just per beta, 1 beta per trial, but per beta for 1 condition in each trial. Is that I'm understanding correct?
Yeah. So in this example, the way we would have modeled it, and not everyone would model it this way, but the way that many people in the field who are doing these kinds of delayed response tasks, whether they were studying working memory or preparatory attention or whatever, but these tasks that have sort of multiple event types, you would model it by getting a sort of a series of HRF-convolved regressors, like 2 or 3 or 4, depending on how many event types you wanted to model. And you would get 1 beta for each event type across the whole experiment. So you would get a map for sort of the Q period, you get a map for the anticipation period, or here the delay period. In this case, you get 3 betas for each trial in this model. So every trial gives 3 betas. If there are 100 trials, you get 300 betas, plus betas for all of the other things you put into your model, the regressors of no interest.
If I'm using the LSS approach, then I will need to do the type times the trials number of the GLM. Is that right?
Oh, yeah. So, yeah, in the LSS approach, and maybe I could try to, if people are interested in the LSS approach, I could ask Jeanette if she would let me post her code. It's just a MATLAB script called LSS.m, and it builds the LSS model from a 3-column file of FSL regressors. So it just takes the regressors you have and takes what would have made your standard univariate GLM and creates all of the GLM models you need to run and then runs them for you. We do have it implemented. Like a postdoctoral fellow who I've been collaborating with has implemented it for SPM, but I don't know if the code is ready to share for that. But it is possible to just take a standard GLM that you already have built, and you have these onsets and durations and stuff, and then just convert it into either the LSA version, which is what I call the trial-wise GLM, or this new LSS version, which will then run a lot of GLMs. And it seems like it would take hours and hours to run them all, but if you relax some of the assumptions, like you don't do all the pre-whitening and stuff, the restricted maximum likelihood estimation step, that's really what makes SPM models take a long time. If you just take that out, which is reasonable to take out because you don't care about within subject sort of T statistics, you just care about parameter estimates, effect size, then it runs super fast. Yeah, for the whole brain. Okay, so it's just a little after 5. We want to get through some more of these 2 truths and a lie. So.